in the sense that that's a characteristic of the digitizer. That's not depending on that does not depend on the range in which you produce an analog signal. It depends on the particular digitizer, right? So this digitizer that we have is a 0 to 5 volt 12-bit digitizer. So that means its least count is actually 5 volt divided by 4096. So now the resolution cannot change. But I can go for a different device, which is probably having a range, this 12-bit digitizer, but in a range of 0 to 1 volt. And then, yes, then my actual precision will go down. But the number, this unit, the digital number, still remains from 0 to 4096.
Yes, sir.
The precision will go up, right? Not
Yeah, so precision should go up.
if you use a 1 volt.
No, so precision has gone up, but now you have a different digitizer. So with the same digitizer, you cannot change the precision. For example, this digitizer has a precision of 1 millivolt, it will always remain 1 millivolt. It doesn't matter how you change your analog part of the circuit, right? If you want to increase the precision, then you have to go for a different digitizer.
Sir, how, like, if you have a number, then we'll have, if you take a 5 volt one, we'll have 5 by 4095. But then if you take a 4 volt one, we'll have 4 upon 4096. Sorry.
Yes.
So, isn't the resolution changing? Like the least count is changing, right?
Least count is changing, but you cannot compare
That
these
is a
two because
different
these two are
device.
different devices, right? It's not the same device.
Okay.
I mean, it's like, for example, you take a scale, which is a meter scale, and has the least division of 1 millimeter. And other way around, I go for a screw gauge, which has a least division of 0.05 millimeter, right? Of course, the screw gauge has a much better resolution. But then I cannot compare a meter scale with a screw gauge in the sense that these two are completely different measurement devices.
Okay, that way, yes, sir.
Right. I cannot increase the resolution of a meter scale by more than 1 millimeter. Similarly, I cannot increase the resolution of a screw gauge by more than 0.05 millimeter. Right. Once I've made a device, I'm restricted to whatever parameter it was made for. Yes.
Sir? Sir, is the circuit like this, that there is a 5 volt battery across all the complete that resistor, and there is a sliding pin, just like the jockey
yes. That's what. So at the two ends of the potentiometer, you connect 0 to like 5 volt and ground, and then the slider one will give you the voltage difference, right? So if it's in the middle, you will get 2.5 volt, and that's why I said that our baseline signal is actually 2.5 volt, which we then take reference as 0, right?
Yes, sir.
And the variation will be on top of that 2.5 volts.
Yes, sir. Sir, we have connected a, we have, there is a thread. So isn't there a possibility that the thread may be slipping and it may lead to error?
Yes. So these are the things which are then going to lead to, well, basically distortion in your data, in the sense that to what level of accuracy and faithfulness one is now able to convert this mechanical oscillation into electrical one. Yes. If the thread slips, right, then basically your pendulum is moving, but since the thread is slipping, the potentiometer may not move at all, right? And that's what you will see then. So if the, for example, if the, because of, continuous operation, the thread has some elasticity, it will, because it's tight, so it will keep, it's always in a stretched position. After a few cycles of working, like 100, 200, 500, 1000 cycles of working, it will become loose. And once it becomes loose, it's not going to transfer that mechanical motion faithfully to the rotation of the potentiometer, right? So these things you will be then able to see in your, when you record the data, right? And that is why it's also important that you keep calibrating your setup, in the sense that, see, we know, so once you have made this thing, once I have covered that box, it becomes sort of a black box. Mechanical motion, something happens inside, you get an electrical signal out of that. But then at regular intervals, one need to confirm that whatever is the mechanical motion, the electrical output or the measured output corresponds to that, right? We do not just blindly go for the plot and forget about everything else. For example, if I start my data acquisition and I have not moved my pendulum, and still I start seeing oscillations, right? That means there's something wrong in the system. I cannot blindly say that without doing anything, the pendulum moves. Right?
Yes, sir. And sir, what was that smoothing algorithm? Matlab, why did you use it?
Right. So, okay. So this part is clear that, how we convert to this thing, right? I mean, this is a very simple technique of conversion. And, but this is the one which is used most often in many places. Again, because it's very simple. So one can easily apply this, right? Now here what happens is, so let's do one thing, right? So now let's make a measurement so that we can sort of see that smoothing thing, like why it's needed, right? In fact, this is the data that you are supposed to get. Okay, so let me just start and start taking data. Right. So now what I'm doing is I'm just measuring this. So the pendulum is moving, it's coupled, so you will get this fast oscillation, you will get the slow overriding oscillation because of the energy transfer between the two, right? And then this is the data which has come. Now what will happen is this data that we are taking, right? It basically corresponds to this 0.2 or 0.4 volts change, right, in time above that mean value of 2.5, which then we are digitizing. So we are getting some number, and then that is being transferred to the PC, right? So now again, that this entire scheme need not give you very, fairly repetitive measurements every time. Like, there will be some jitter on this. It's called jitter. That so, for example, ideally, every time, let's say at regular time intervals, you expect, let's say, 0.15 volts, right, at some point of time at regular intervals on this plot. However, it could be converted to 0.15, it could be converted to 0.155, 0.152, and things like that, right? Depends on the resolution and, again, all these factors. How well the potentiometer pod is able to reproduce the motion of that pendulum, right? So if you take the data like this, let's say stop the measurement, then basically this is what we get, right? So we get this oscillatory behavior. However, I mean, there are these, for example, it's more visible at the peak values. You will see this kind of jittery things, right? Because another thing that is involved here now is, so whenever you digitize something, right, another factor that comes into picture is the measurement time period, right? So this 4096, this 12-bit, right, it converts and all that, at what rate it is doing, right? So anyway, so you get this kind of, these multiple points, which are overall, which are representing that trend, right? But otherwise, there could be different individual fluctuations while you measure the same point again and again and again, right? For example, this peak, the central peak in all these parts is supposed to give you the exact same value, other than a decrement in the amplitude because of friction and all that, right? However, not every time you will get the exact same value, right? Because, I mean, you have 1 millivolt precision, right? So there could be a few sort of points here and there. So yeah.
Sir, is this smoothing algorithm something like fitting the curve? So there are certain points which do not, in the very shorter range, if you focus on the peak,
Yes.
say,
Yeah,
then
so not fitting, we do, I mean, it's not fitting, it's actually averaging. So what you say is, in fact, it also relates to, the question which was most often asked in regarding home assignment 2, that this was not mentioned in that assignment sheet, that you should take multiple readings and then come to an average value, right? What we are doing here is exactly the same, because we expect the same value here, right? But that's a critical thing. My system is not ideal, right? So to establish that I have a faithful measurement there, what we do is, so in this case, this will be called smoothing, in the sense that what we'll say is that all three, so we'll take every point as the average of 3 consecutive points, right? Because that would, to certain extent, take away that jitter, right? So that's called the smoothing. Now you can do 3 nearest neighbor smoothing, you can do 5 nearest neighbor smoothing, you can do 7 nearest neighbor smoothing. It depends on, which way you want to smoothen and what sort of data you have, right? Because for example, if let's say if I have this kind of curve where I'm trying to look for a variation, I can run a smoothing algorithm on this. I can say that, okay, fine, let's smoothen the 3 nearest neighbors, right, and take the average value to plot my curve, right? That is fine. Somebody would say, but doing it for 5 points would give you much better smoothing. Possible. However, what you have to worry about is in taking 5 points and taking the average, are you going to miss out on the qualitative features of that particular curve? Because maybe in the between the 5 points, you actually have the system changing its properties, right? For example, if from here to here, if I only have 5 points, right, it does not make sense to smoothen that, because then that way we are just going to lose information regarding the amplitude and change in the amplitude. However, if right on this peak, if I have 5 points, then I can easily take an average of that. That just gives me average value of the maximum amplitude.
So, sir, in smoothing, basically, you're saying that there are, we say X point smoothing, it will take successive X points, it will take an average, and then
Yes.
for all these sets of 5, all these sets of X, it will actually join those averages.
Yes, yes.
Okay. And it's so like, can you give an example here? Like, can you show the 3-point average ones?
So I cannot tell you like which particular smoothing this does, because it's all inbuilt here, right? However, for example, here, if you can see this slider, so I have run the smoothing tab. So this slider, right? So this slider will control what level of smoothing we are looking for. Could be 3 point, could be 5 point. So that's internally written in the script. But this is how we can actually control how many points we need to take for, or we want to take for smoothing the curve.
So, sir, it's actually a moving average, you want to say?
It's average, yeah. Smoothing is just averaging, yeah. So all that matters is which way you are averaging. And here it's just point-wise averaging. So there is no greater detail.
So it's not visible actually so much.
Sorry, what is not visible? No, this one I am just going to change, because this is the size of the line. So this is a smooth end one, and now you can see that basically it will take care of the jitter. Right. Well, a lot of things. One is your resolution. Second is your mechanical setup, which is converting this oscillation to electrical signal. Then the stability of a resistance, stability of your 5-volt power supply. All these things will lead to the inaccuracies in measurements which you expect to be identical. Right? So jitter is the uncertainty or the error, or the change variation in the measurements where you expect identical results. Right? Otherwise, for example, these oscillations are not jitter because we expect the oscillation. We expect the oscillations at these particular frequencies. But if I expect the amplitude to be something, and then over different cycles beyond that frictional damping, if I see different amplitude, let's say peak values, then that corresponds to the jitter or the uncertainties because of the experimental scale. Yes.
Sir, what caused, like in this graph, like we see the third and fourth parts are like weird, not consistent. Like why is that?
This could be just because the system. So if you look at the pendulum, right? So all you have to do is, so that's why first one has to, before looking at the data, right? First we should look at our actual system. For example, this is my actual pendulum, right? Now this itself has variation, and itself has parameters which are not under strict control. For example, we take this as a 1D pendulum, right? So when I move it, it's supposed to be a 1D pendulum, right? However, there could be motion in the perpendicular direction. Now that motion is not under my control, right? In fact, that's a different level of coupling. It's a different level of coupled motion, right? And then that will control at a different, with a different frequency, characteristic frequency, the energy transfer, right? So what you see here, one has to then take this for much longer time and see if you can find a repetitive pattern in this behavior, right? And then that could just be coming because of the non-1D character of your coupled pendulum. So these things, I mean, so there could be various reasons for looking. And the important thing is, once you have an observation, you should try to see that all the observations that are out of ordinary, that we do not expect, can we associate either a random, either a systematic, or kind of uncertainty to explain or to understand that change. Because if not, then one has to worry about the system. That you expect something and it's not conforming to your observation, right? Then that means something is wrong with the understanding.
Yes,
Sir,
sir.
here in this case, sir, the jitter will be due to the friction which is also present. So here, when the total amplitude is going down, like for example, at time equal to T1, we have an amplitude A1, and then at time equal to T2, that's amplitude is A2, which is lesser than A1.
Yes.
So that is actually the jitter.
Let me just go back to the plot.
Can you just point out few examples, like on the graph?
No, that is
Exactly.
damping. That's
That
what I
is
said.
damping.
This is damping. So, for example, on
No,
this
but
one,
in
like,
beats,
sorry, these are oscillations, right? So now these are already smoothened out. So if I go back to the original one, right, the original measurement.
sir,
Yeah.
but over here, these the change in amplitude is not due to the damping. It is because of the beat phenomena, no?
No. So there are two changes. One,
Sir, the
so
local
let's-
ones.
yeah. Let's focus on this one, right? The first envelope, half envelope, right? Now here, if you see, I mean, I can actually see quite clearly. I'm not sure if it's visible there, right? If I look at this, let's say 1, 2, 3, 4, the fourth spike, right? This one.
Mhm.
Now
Yes,
this
sir.
corresponds to the maximum amplitude of a single pendulum, right?
Yes, sir.
Here is the amplitude is maximum. However, this is not a smooth curvature. There are spikes here, right? I mean, let me try to bring it slightly more closer if it makes it more visible. Right.
It's not clearly
So,
visible.
let's
Sir,
try
it is
to-
pointed only that you are saying now.
Yes.
Sir, that much is
So-
visible.
Right. Yeah. So now see, these are, so there are spikes here, right? So basically what it shows here is, let me see if I can actually zoom it out. This is what we can do. If I can zoom it out, now this is, it doesn't have zoom function. Display area, yeah. Let me see. I want it to be from 20,000. Right. Yeah. Now I think it's a bit visible, right? So if I point on this one, right, this is supposed to be the maximum amplitude. I mean, at least in this cycle. Now, if you look at here, you can see these sharp spikes,
Yes, sir.
right? So now see, in terms of the pendulum, right, what you expect is its amplitude. I mean, so let's say if I only consider this sinusoidal cycle, this single cycle, right? I expect the amplitude to go increase in one direction, come back to mean position, increase in other direction, come back to mean position, and go like this, right? However, if I now look at this extreme position, I can see that in terms of signal, I have a spike, reduction in the amplitude, very small, but reduction in the amplitude, and then again a spike, right? Now, the pendulum doesn't behave like that, right? It's not going to go like at the extreme, it's not fluctuating there. So this is now the jitter because of the conversion of the signal. the motion of the pendulum we actually expect to be much more smoother compared to this. Right?
So
So
you're
this
saying
is the jitter.
the red
Right.
colored part, sir.
Red color. Yes.
As in it basically there's like a line in red and there's a dark region in red. So that part is like a spike up.
Right. So that dark region which you are seeing is the jitter at that extreme position. Right. And it's there for every other position also, but it's just more spread out. So it looks like a line. That's all. Right. So these are then the fluctuations in the measurement. Right. And you can see that they are like not very large. They are not, so compared to the oscillatory behavior, it's not like overriding that. So your data is not that bad. But yes, when you're looking at it at one point, there is fluctuation, and by smoothing, that's what we are sort of smoothing out.
Sir,
Just to get a more faithful. Yeah.
sir, can we say that at the darker points, we have more number of plotting points? Like we can say the 4096 points that are that we get for the 0 to 5 range can be plotted on a graph and we can make a continuous curve.
Sorry, whose this thing is on? No, so again here in the same time interval, you are taking exactly the same number of points, right? That's the rate at which the data is converted from the system to the PC, right? So now you see this as darker and lighter is because, see, in the same time interval, this is something here, right? Your amplitude is actually changing from here to here, right? So, and since the jitter is very small, like even here, if you see the jitter is only in this region, you don't see that jitter here. It just becomes part of your falling amplitude or falling voltage value. Whereas at the extreme position, right, at the peak, at the extreme position of the pendulum, what it does, its speed is 0, right? So it's not spending same amount of time at every location, right? So you basically have more data points here in that way, and that's why the data points are not, very well separated. They are all around the mean position, and that's why you start seeing the jitter and bunching of these data points here, which then shows us darker, darker regions.
Yes, sir.
So, and in fact, that's what we are doing. All we are saying is we know that the peak or the mean lies somewhere here. So let me just average out the values here and like give a mean value for the time, because I want to find out time period.
Sir,
Yes, if you decrease the resolution, in this case, there will be less data. In fact, by smoothing, that's what you are doing. Right? When you say I'm taking average of the next 3 points, I'm decreasing my resolution to 3 millimeters instead of having 1 millimeter.
Sir, I had a doubt in the manual.
Yeah.
In the manual and what you've written on the board in the lecture, there's some differences.
yes, sir, there is some inconsistency because, sir, you have assumed omega CB to be different than what that is written in manual.
So actually, in the omega c on the board in the lecture, you've written omega c is equal to root over of g by l plus the kl for that term, and in the manual there's no g by l in the omega c. There's
But
only
that's
one
just a
term.
matter of notation, right?
But then the answers are getting the omega positive and the omega negative are the same, so that won't be possible for different omega c and omega naught.
Yeah, that is the case. And sir, there was some problem with the this differential equation, sir, that you wrote. Sir, differential equation should have been theta 1 double dot is equal to omega c square theta 2 minus theta 1 minus theta 2 omega 0 square.
So, okay. So this differential equation is anyway being covered in your course, 1 or 2, right? You guys have already done that part.
No, sir, we haven't done it yet, but we studied.
SHM has not been taught yet?
No,
No,
sir,
sir.
they haven't been.
Oh, okay. over the whole mixture. But anyway, this will be covered there in like complete detail. So you can, so you can take that analysis. I'll have to look back. I might have copied something wrong from the manual. Right. But anyway, I'll have a look at it. And if there is something missing, then I'll post it on the forum. Otherwise, this analysis will anyway be done in the SHM part of your PHY 102.
Yes, sir.
Hmm.
So in the manual, we have taken that conservation of E dot energy, derivative of energy.
Hmm.
So why have we taken that instead of conservation of energy?
That same, I guess, because energy
No,
will be
we have taken
conserved.
energy only. E dot is 0, right? So we say that total energy is not varying with time. That's all. Okay. Yeah. So there are a few raised hands. Do you guys have already asked the questions? Yeah, sure. Go ahead. Mass of what? Mass of the two bobs. This is something that you need to
Sir,
analyze.
sir, as you told, sir, omega B is related to omega. I mean, the coupling strength is related to omega B. Then, in that case, mass should affect the coupling strength.
No, I mean, if you just consider it more intuitively, yes, because I mean, so whatever we have done is assuming that the two pendula are identical, right? If they are not identical, then well, the coupling is not the same, right? Even though the coupling agent is same, because the way we describe coupling was how the energy is being transferred from one system to other system. That does depend on the response of the other system. And if the response of the other system is not identical to the response of the first system, then the analysis needs to be modified. Because then
Sir,
you do
but
not have. Sorry.
Sir, but omega B will still be this. I mean, omega B will remain the same for not like if you change the masses M1 and M2,
Yes.
you take them to be different, and you calculate omega B for one experiment, and that will be the same, right? For that one experiment, you take different values, not values, for different times.
Yeah.
You measure that omega B, but that will be the same, now.
Yeah.
So the coupling will the time it takes to transfer energy from one mass to another mass will remain the same. So why does that differ? Key coupling strength for one will be different. Coupling strength for one M1 will be different from coupling strength of M2.
No, I'm not saying it's going to be different. I'm saying this is something that now you have to analyze. That where the mass plays a role. See, so far the analysis that we have done, right? All we did was we considered omega naught. Right? In writing down the equation of motion, we are only interested in omega. And in case of the simple pendulum, omega is independent of the mass. Right? So now with the combined system, one needs to see if that still holds. Yes. 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 I mean, observationally, I can show you different ways of doing it. And then in one case, it will seem as if it doesn't affect. In another case, it will seem as if it does affect. Right. For example, a very simple experiment. Right? What he said, let's make this infinitely heavy. Right? And to do that, what I need to do is I just need to hold it. And now you can wait to see the beating if you can. Right? And then as soon as I leave it, of course, it will start to have the energy transfer and all. So these are the questions that you should think about and you should try to find answers of. I mean, one part of experiment is what we have shown you or what can be done in the lab. But then this will lead to many more questions and observations that are up to you to do or to find the answer for.
Sir, so when one was infinitely heavy, there was no energy exchange between them, right?
Well, it looked like that. One does need to actually now look at the oscillator behavior of the moving pendulum and then see if it follows exactly the same thing as if there was no coupling or if there is any other difference there. But at least I mean, in the short period, at least I could not see any change in the amplitude per se. Right.
Sir, I believe ki if one of the masses will be infinitely large, then effectively in the formula in place of m, like KL square by mgl that we were writing, and if we write in place of m the reduced mass, then reduced mass will be effectively the mass of the larger mass, and yes sir, it just increases the time period, and it shouldn't be like there won't be any energy transfer.
I mean, yeah. I mean, all comments here will be valid at the moment, unless somebody comes up and says, no, that's a wrong explanation, and then you give the correct explanation. Okay.
Sir, I did not understand how for the estimation of K, how that formula came. Under root of 2 omega B by omega naught. Why?
That thing is given in the manual. How do you get this?
Not given.
Must be given in the manual. I mean, anyway, what we are doing is we are just finding out the ratio of these two frequencies, which can be measured, which we measure from our thing. We have the expression for omega b, right, from the differential equations. We have the expression for omega naught, right. So all you have to do is just write down omega b over omega naught and see if you can get this particular kind of relation.
Is this formula true only for weak coupling?
I mean, this formula right now I am applying for weak coupling. Yes.
Okay.
And then where that coupling strength being weak or strong becomes distinguishable. That again has to be seen in terms of analysis. Where we can make that kind of, from where we can start making that kind of approximation. Right? So basically K by M, square root of K by M in terms of omega naught. What is that ratio under which one can call it either weak coupling, or one has to go with a more exact analysis and get this convoluted coupling kind of thing.
Sir, I have one of my doubt remaining at the forum related to linear air track quiz question. So can I ask here, or will it be replied on the forum?
I mean, it will be replied on the forum. Doubt regarding quiz questions will always be replied on the forum.
Sir, I wanted to ask about my home assignment, sir. It has not been graded yet.
It will be graded. I think around 18 copies are left. Around 18 copies are left. I'll ask the TA to finish it.
Okay. Okay. Thank you.
Home assignment 2. Well, go ahead. I mean, there are no more questions on this coupled pendulum. Maybe for another 2-3 minutes, we can take those doubts. Yeah, go ahead.
Sir, the doubt, sir, still, so a little bit of the jitter concept is still slightly unclear, sir. Like there, the dark portions are because the pendulum is staying there for a longer time, and those complete variation from like one portion of the dark portion and then the to the other side of the dark portion is the jitter, right?
Just a second. Let me reduce the range even more. Right. So let's go from, let's say, 6,000 to 8,000. Yeah. Right. So now you can I'll just change the camera. Yeah. So now you can see this.
Yes, sir.
Yeah. So you see these spikes which are coming, right? So you expect the amplitude or the whatever the voltage value to go down smoothly, right? Because the pendulum is going in one direction. It's not going like it's not sort of vibrating around any given position. It's going from one swing to another swing. Right? That's a very smooth motion. Right? However, what will these spikes correspond to? These spikes correspond to if suppose my measurement is jittery around that location, right? That is like, let's say that over, so these spikes basically in terms of mechanical motion, if at all it's there, these will correspond to some kind of a very high frequency vibration riding on the pendulum motion. So the pendulum is actually making a motion like this, I mean, in time, but riding on this is a very, very fast sinusoidal ripple or a sinusoidal vibration, which is not there in the mechanical motion as such. It's just coming because of the conversion of this mechanical motion to electrical motion. Because one, our resolution is very, very high, right? And it's like 1 millivolt, whereas the signal here is of the order of 0.2 volts or 0.3 volts, right? And then, and other things are this motion of the resistance and all that, right? The context and everything will play a role. So instead of getting, a smooth variation from here to here, what you get is you keep getting these values which fluctuate around that mean.
Yeah, so okay, so now I understood what you meant by spikes. I thought those dark regions are spikes.
No.
Actually, sir, the image quality here, I was not able to understand it. That's
right. I mean, that's a problem with the online mode of doing all this.
But sir, why is it now? Now you have answered the question about jitter, sir, and now have understood it completely. But now, sir, my doubt is, so why is it so dark? Like it's instead of a line, it's like a complete patch. Why is it so dark, that reading? Is it like, why is that the case?
No, it's just the way you are. No, it's just that time range. For example, if you look at here, this is about 8,000. I mean, in terms of time, so about 8 milliseconds. And then this is about 9,000, right? So in 1 second, basically, you have this complete change, which is now going from 4.15 to approximately 4.3, right? And now you compare that again with this region, where here this is something, let's say, around 9,500, and this is about 10,000. So half of this entire region, right? However, the change in voltage is approximately from 4.15 to about let's say 1, right? So you have a much smaller change in typically the same amount of time. So all those values are being bunched. They are represented as if they are bunched together, right? So this seems much more darker because here it's more spread out, right? So for example, here in this 1 second, the value goes from 4.05 to up to about 4.4, right? Whereas now, for a good 50% of that fraction, the value only changes from 4.4 to, let's say, 4.36. So this region seems darker compared to this one. Right? And then again, the jitter here is at the same level, corresponding to all these values. Whereas here, the jitter is the same, but the values are varying too much.
Okay,
So the jitter actually forms the
bunching.
line itself.
Okay, so it's because of the bunching. Okay, okay.
Right, right. So I mean, very quickly, what we can do is we can change it even more. So let's now maybe try for something like this one, 1100. $11,002. Yeah, right. Yes. You can see this. So now I have shown you like one rise, right? So this is how you see the data. You are expecting a nice sinusoidal waveform, right? What you are giving it at every, and this is taking like 1,000 points in between. In this range, it's taking like about 100 points because 1 millisecond. So each division now is 100 milliseconds, and my system is taking data at like every this thing. So at every millisecond. So I am getting too many points here, and those are like all the points are basically around this mean. So I can fit a mean curve here, but then the actual value is going to deviate slightly from that mean. So this is the jitter. And if you expand it, now you can see it's the same level as your bunching things. I mean, this was your bunch region. Now this looks as clean or scattered as your rising region. That is a display thing. How much you are showing in the same frame.
Sir, in EMI experiment, we had same sort of values around x-axis that the values were positive and going negative. That was also corresponding to these jitters.
Sorry, in which experiment?
So in EMI experiment, sir.
Yes, so around that zero, right? When the system is supposed to cross that zero value, you will see that there are fluctuations about that zero value.
Yes.
And that is because of this thing. Because there also it's the exact same way you convert this mechanical thing. I mean, so there it's not purely mechanical because you are actually getting the EMF out, but you are basically digitizing it and then storing it in the PC.
Yes. Thank you.
So,
Okay. Yeah.
I had a doubt regarding how to take the measurements and all. Like when we do the home experiments, first of all, like there's a very short range of time for example, in the home experiment 2.
Yeah.
So there's a curve or something that comes, and we were supposed to take the time or something like that.
Yeah.
So, like for example, even in this experiment, there's a damping in it, right? So after
Yes.
some time, it becomes a little consistent, like it becomes constant a bit. But in the first few seconds, there's a little higher range. So which part should we take the reading from?
So if you know that the system is going to stabilize, then you will take reading when the system has actually come in that range. For example, I know that after I let it go, right? Initially there will be some disturbance because of my hand and all that. So I should not take the first few cycles. The system, because of damping and this friction and everything, the system will settle down into a 1D motion after a couple of cycles or 4 or 5 cycles, right? So I start taking the measurement beyond that. So this is one. Second is, so I mean, again, most of you, I mean, I understand that's a valid concern, but it's not something regarding the marks. It's about how do you understand the experiment and data reporting. You cannot make a single measurement and say that this is what is the is the truth in the world, because nobody is going to believe it. So every time, first you have to convince yourself that whatever you have measured is repeatable, right? I mean, we always say in physics, all experimental data has to be repeatable. Repeatability is very, very important. And because it's whatever you are performing is under the laws of nature, and they are not going to change from measurement to measurement. Right? And what is the way of validating that? What is the way of saying that yes? I mean, when we say that the simple pendulum, the frequency is simply square root of G by L, right? Not L by G. Yeah, G by L. Sorry, L by G. L by G. So what is the validity of that? Somebody says, fine, I'll make a simple pendulum. I'll show you that the frequency actually comes out to be square root of L by G. But then Why would you believe that? Unless you can also do the same thing with the same setup and get the exact same value. So anywhere you perform the measurement, any number of times you perform the measurement, the laws of nature are not going to change. So you are supposed to get the same result. And of course, we understand that experimentation is different than theoretical analysis. So there will be unknown errors into system. So to get to a mean value, one does need to perform same measurement again and again, and then come to a value which will have some level of confidence in its in terms of its quantitative weight. So that is why that repetitive measurement is very, very important. Now, how many times you have to do it, which one can be validated and all that. For this, I had uploaded one short, supplementary quiz kind of thing under resources. And if you actually go through that, perform the tasks that are listed there, it might just help you in figuring this out on your own. That why 3, why not 5? Why 5, why not 3? Right? In which situation I should take 3 measurements and I'll be okay in reporting that value.
Okay, sir.
Sir, I have a
last question.
Sir, I have a doubt a little regarding this course, that home assignment. Sir, could you, sir, I have a request regarding this, that could you provide the correct template regarding home assignments? Because we do lose marks sometimes just because we don't write. For example, in home assignment 2, we didn't write acceleration in X and Y and Z. So if we are not aware about the correct template that we are given in according to what we have to mention it, the marks are deducted like that.
So,
this is a
yes. So one thing is we deliberately we do not want to give a template because we want it to you to figure out which way you should report your data and such that it contains all the information, right? And so, for example, in the simple pendulum experiment, we gave you some kind of a template. In fact, all your lab manuals which we are uploading, they have some kind of a template. So that should be able to provide you enough hint on how to, sort of make your observation tables and all. Particularly with the home experiment 2.
Mummy.
None of you had reported this AX, AY, AZ values, right? And if you use acceleration with G.
Sir, you should have told us to upload.
No, I don't have to tell you. If you use acceleration with G subroutine, I am not able to understand how you can find out the average acceleration without, going over that analysis. And if you have gone over that analysis, then why would you not report it?
So in discussion, then ask that doubt.
But then you don't deserve marks because in the assignment file, it was specifically written that use acceleration with G.
So but in the discussion,
In the last discussion.
yeah. Absolutely.
Yes, sir.
Yes, sir. We
Well,
are
you can use it to confirm your results.
No,
But
actually,
as far as the assignment template is
Sir,
concerned,
he
Instead of
told to use the
subtracting
value.
us to use
G.
that because with acceleration with G there was some error coming in the
no, there is no error
assignment.
coming.
so there was
No,
an
with G,
sir
sir,
said
you will always get a value of acceleration around 9.8, which was observed in the case of an inclined plane. Like I tried it thrice with G, like I use a subroutine with G,
Yes,
and
sir.
I got it 9.75 thrice. While by calculation it should come out to be somewhere around the 2 or 1 point something.
Yes.
So
So
that
instead
was
of
it.
subtracting 9.8 sine
So
theta
it's-
and cos theta,
I
we
have
can
to-
directly use
I have
without
to-
G.
Yes,
All
sir.
reaction
I had
is
uploaded the grading scheme. Just go over that. It shows you exactly how to get the acceleration using acceleration with G subroutine. Right. But anyway, again, now the second point that comes is regarding the grading. Right. See, what I could have done is I could have made all of these assignments out of 40, given you 20 marks for submitting the report, and then cut down 5 marks for these things. Right. It's just a DC shift. So the idea is to make you aware that what is important while reporting the data. Right. I mean, I do not think that you should worry too much about losing 5 marks here, 5 marks there. We are just going with a more coarse grading scheme because then the grading remains, to a fairly good extent, it remains uniform. And if you just want to see marks on your report, right? I mean, I understand that is a psychological issue. If you just want to see marks on a report, I can always add 20 marks DC to everybody's report, right? So do not worry about that too much, but try to understand the spirit in which data needs to be taken and then data needs to be reported. See, it's your job to convince the person that you have done the experiment and what you are reporting is absolutely correct. right?
Sir,
Or
can I
absolutely
ask
safe.
something? So, apologies to interrupt. Just can I ask something?
Yeah.
Sir, when we use acceleration with G graph, I think we can use only the Y acceleration graph to predict the acceleration of the body of the phone. Because what I will do is that first I'll hold the phone on the inclined surface, and I'll see what acceleration is the like I'll start the measuring of acceleration and I'll see what it is giving, and then I'll release it, and then I'll get another acceleration and I'll subtract both of them.
Yeah.
So that would be the acceleration along the Y axis. And because I
It's an incline, there will be two axes involved.
No, sir, because my phone is actually the Firefox app keeps the y-axis along the phone.
Sir,
Like
it keeps
my phone
y-axis
is
along
also
the length of the
inclined,
phone.
right? So my axis become inclined along with the phone, and that is why my motion is only along the y-axis. Phone's motion.
Yes,
So-
sir.
Yes.
sir, it gives the accurate
Unidirectional.
So yeah, Praveen, so G is acting perpendicular to the ground, and that's why when I'm going to hold the phone, what I see is that instead of showing a 9.8 along the y-axis, it shows some component like G sine theta along the y-axis and G cos theta along my x-axis.
Z-axis.
Sorry, z-axis. Yeah, right.
So
And that
what I
is
do
why.
is, yeah, I understand, and it's a good discussion, but let it be among yourselves. You have the phones, you have the Firefox app, and you have both the subroutines. Why don't you guys just try taking data with both the subroutines? And what you know is the data has to be like the average expression value has to come out to be correct, right? So just figure out for yourself what should be the scheme for this. I think we have exceeded our time by quite a good margin.
Sir, I wanted to ask sir one thing.
Yeah.
Sir, I wanted to ask that, sir, my marks have been deducted for calculating kinetic coefficient of friction. Right. Coefficient of kinetic friction. Yes, sir. In my assignment, sir, and they said that it was not required, sir. But I believe that, sir, it was the very essence that we have to calculate coefficient of kinetic friction in the experiment.
I can have a look at it because sometimes one has to interpret.
Also,
Yeah,
sir,
sir,
will-
same doubt to me also.
Sir,
will
I
nor-
have like
will normalization
posted a
happen,
forum.
sir? So will normalization of marks happen because few tutors give slightly more marks to other students who have done the same error as us?
Yes, yes, yes.
Yes, sir.
No, nominal marks will always happen. This time we'll probably not need to make it too much, but we'll still do it. Because, for example, I know that, if we go with the scheme that I have uploaded, none deserves 20 marks. Right? It does not mean that you guys have not put in effort. It's just that if you stick to a grading scheme, nobody should be awarded 20 marks because there are always some things to learn. And then some TS have given 20 marks, some have stick to 15 marks, right? So those kind of things we will take care.
Okay, so normalization will fundamentally occur.
Yes.
Okay, sir.
Yes. Yes. No, the thing is, you cannot find out this maximum inclination beyond which slipping starts to occur in one measurement, right? I mean, no, that's all. No. It's a data measurement. You will have to repeat the measurement multiple times to say that this makes sense. I mean, no,
Sir, but it was-
ever believe a single measurement made by you. Right. Again, it depends on your judicious choice, like what you want to measure or where you just want to report the error and things like that. Right. But
Sir, just
yes,
from the
whatever
next time,
major-
make sure that you ask, give everything which you have to
So
ask.
if I
sir,
give
or
you
else-
everything, then where is your input coming in?
Sir, no,
See,
sir.
because
How will be able to read the minds that we have to write AX and AY,
Why-
sir?
No, you have been doing experiments till class 10. You have been seeing so many of experimental reports. We are uploading all the manuals. So there you see, some table, something where you have to put in things there, right? So that's okay. This is a learning process. There's nothing
Can
like,
it be
if you have
considered?
not done it this time, then you have missed on something huge.
Yes, sir, can it be considered for this time? Because we just consider acceleration along the plane, and like seeing the axis orientation on Firefox, we realized that it's only the AY that is required. So that's why we did not write AX and AZ. So can it be considered this time? Because it would
Yes,
we
sir. Some of
we
the
thought that it
even
wasn't relevant.
yes, sir.
Yes, sir.
Use
that.
Yes,
That-
sir,
In my
absolutely.
error analysis, I've even mentioned that I've taken the standard deviation of the reading and even given the graph for the axis.
The absolute acceleration gives us the acceleration along the line of motion only. So we don't need to consider any Y, Z or something.
Yes, sir.
No, but then you'll have to take it again, right? Because there's some disturbance in the start of the motion.
You have to take it repeatedly. Then only you will be able to find out what is the mean value.
Yeah,
So
we
the
were
key
trying to
for
take
this
AX
one
and
is,
AZ0.
yeah.
See, again, do not worry about the marks. As I said, there will be a bit of normalization will anyway be there. And how much this matters and all that in the final grading scheme is still not, you don't know it. I also don't know it. Right. So I mean, these are going to be gross bins. These are not going to be like 1 mark, 2 mark differences which are going to count and all that.
That's what, sir,
The idea is that by doing something hands-on and without any help, because we are not, and that's why we are not giving you any template and things like that, so that you start thinking in that way, that when I am designing an experiment, I am performing something, I am reporting something, what is relevant, what is not relevant, based on what all you have learned so far or what are you are learning in different courses. So if you take it in that spirit, I think then our job will be probably done to some satisfaction. Marks and all are not really that critical. I mean, I can tell you, these marks are not that critical that you should worry about it too much. But yes, try to improve on whatever you have missed out so far.
Okay, so
Sir, one last question.
Is
Yeah.
if there's any such situation, like ahead, like let's say about AX, AY, and AZ, so we'll have to include all of the readings even if we don't include them in the calculation.
Yes. Whatever you measure, you have to report that measurement like absolutely faithfully. That this is what I measured, this is what my device is. Now, what I use out of that is completely different, right? I mean, because I know what is relevant, what is relevant. वो formula में ही नहीं आ रहा है तो उसको डाल के क्या करना है? But when you are reporting, see, an observation table is an observation that you are performing, right?
Okay.
You cannot omit out things from that observation table.
Sir, on one end, we are supposed to be quite creative in how we are supposed to report our data and all. And on the other end, we are supposed to be graded by a fixed grading scheme. Doesn't that seem quite conflicting?
No, because your creativity does not mean that you can, you are not going to learn the scientific process. You can be creative while sticking to the scientific process. So we are not asking you to write a 2-page report and all that because we don't find it, too important. But if somebody writes, that's not a bad thing. We'll not say that you are cutting your mark because you have given a 1-page explanation of what you have done.
Sir, one last question. Sir, I have taken 5 observations, but even then they have written a remark that take more readings. I have already taken 5 reading and it was written that at least 5 readings should be there. So for next time, should I take more than 5, even if it is given at least 5?
No, I mean, I don't think so. I mean, see, again, the thing is, this might depend slightly on the graders. So if it's a big issue, then I can have a look at the particular answer sheet. In fact, I have done that also. At times, I keep checking randomly, and there are some mistakes in the grading. I do correct it on my own, right? So that's not the case. I mean, see, you should understand what is needed. Repeatability in the measurement is definitely needed. You have to perform the same measurement again and again to establish its validity and faithfulness. These are the main points. Now, how many numbers you take, how many readings you take, these are again left to the experimenter, unless it's going to cause a huge change in the final result. So 3 important, is 5 important, is 7 important. That's a discussion which requires more thought. So for that, I will still urge you to go through that questionnaire sheet under resources, food for thought. Because these are the questions which you need to come for the answer quick.
So, here it is slight request regarding the home assignment 2. So if you could go through my assignment, that I've the grader has mentioned that you haven't mentioned the observation table, etc. But I've mentioned it there in the PDF file. But how? But he has not.
See, I can have a look at your getting the.
I have mail also regarding this to you, but I haven't been replied.
Okay, that's okay. I can have. See, I'll take some time to go over all these queries, but I keep checking the reports, and if I do not find too much to change, then I don't bother to either change or to respond. But if there is something that is drastically wrong, then I'll definitely correct it.
Sir?
Yeah.
So I missed out the quiz 2 just because of some connectivity issues at my area.
Yes, I think you had sent an email.
Yes, sir. Yes, sir. I mailed you at the same moment when I.
So I just kept it like as a notice, and we will let you know if something has to be done regarding it.
Okay, sir.
So we'll just combine all these cases over these 4 quizzes, and then we'll take a call on this. We could offer a makeup quiz, or we can prorate them.
Okay, sir.
Sir.
No, we thought of giving you one, but then decided against it. You should enjoy your recess. I think, prepare maybe for other subjects, and then after 10 days, we will give you another one.
Sir?
Yeah.
Sir, can you do something regarding inconsistency in marking? Sir, because I have checked a lot of home assignments done by some of my friends, and I found most of them did what I did, but I got 7 marks and they got 15 and even more than 15 for absolutely same thing. How, sir, is this possible?
No,
And even
that's not
in the
possible.
mark, in the remark,
I'll tell you. For
I have
example,
made.
we have already told the graders that do not give anything between 5, 10, 15, and 20. And that's why if you see the grading scheme, all it shows is you will get 5 marks for this, 5 marks for this, 5 marks for this, and 5 marks for this. There's nothing in between, right? So some of the graders still continue giving this in between number, which we normalize, which we will take care of. When we have the final list, we'll go to the individual ones and we'll either up take it or we'll downgrade it. That's all. If you find that you should have received 10 marks, but you have been given 7, we'll give you simply 10. Right. So that normalization we will do. Another issue that I explained that some graders are giving more marks than what the report deserves according to the grading scheme. So those we will anyway normalize.
Excuse me, sir.
Yeah.
Sir, in my graded copy, the checking मतलब जिसने चेक किया है उसने थ्योरी वाले पार्ट पे 5 मार्क्स लिखे हुए हैं, फर्स्ट ऑब्जर्वेशन पे 5 मार्क्स लिखे हुए हैं, देन आगे कुछ भी मार्क नहीं किया हुआ है कहीं भी. मतलब आगे वाला पार्ट या चेक नहीं हुआ है या मतलब उन्होंने मार्क्स ही नहीं दिए हैं फिर.
Have you written it on the forum?
Yes, sir.
Yeah. Then because what I'm doing is I'm going one by one to the reports in the forum. So give me maybe another week or something. And then
Sir, mine home assignment has not been graded yet.
Yeah, as I said, around 18 copies are remaining, so those will be graded.
Okay, sir.
Okay, so let's finish this for today and enjoy your recess. Right. Have fun, have some relaxation, and then we will anyway we'll post new assignment and new demos after your midterm recess and let you know when our next interaction can be. So, I mean, as part of the course, we do not have anything further on this. Right. However, it depends on your interest. If you want what, because this is what we were thinking initially, that we will offer you one lecture, sort of a live interaction kind of thing, where we discuss the errors related to the particular experiment that we have performed. Right? So connecting the formal error analysis part with the actual measurements and things like that. So let me discuss with our instructors, and if possible, then in the post mid recess part, we can include something like that. Yeah, sure. Yeah,
Yes,
so
sir.
we can try to have that. We'll have some experiments and then look at those experiments and actually see the errors, what kind of errors we are associating with these measurements and all that. Okay, so have a good week ahead.
I think we could just start with a short repetition of what we did last time. We introduced what was known as the Hamilton formalism as an alternative but equivalent sort of framework for analyzing mechanical problems as compared to the Lagrangian formalism. And the bridge between these two formalisms was the so-called Legendre transformation, which essentially consisted of a mathematical way to exchange coordinates. Because in the Lagrange formalism, we operate with the generalized coordinate q, its time derivative q dot, and time as sort of the descriptive variables. In the Hamilton formalism, we use the generalized coordinate q and the canonical momentum p associated with this generalized coordinate q and time. And so the prescription to go from the Lagrangian to the Hamiltonian was to simply subtract the product of the two variables we wanted to interchange. So in fact, we subtracted the product between q dots and p in order to make this
I already did a derivation of this equivalent one-body problem for a two-body problem, but it's complicated stuff, and I wanted to put it down with animations and better equations, and so I'm going to skip a couple steps. I'm going to do everything again, and this is going to be my most complicated video probably ever. So let me just start off with the two-body problem, and this is also a central force problem. The two-body problem says there's two objects interacting with a force that pulls only towards them, okay? Or you could say there's a potential that only depends on the distance between them. That's a two-body problem. So here's the Earth and the Moon. That would be an example of a two-body problem. This is an actual image of the Earth and the Moon, which is kind of strange because I wouldn't think that you'd be able to get a picture this good since they're so far apart, but anyway, there we are. So let's look at an actual two-body problem here. This is not the Earth and the Moon, not to scale, but you can see that they are gravitationally interacting with each other in some complicated way, and there was my mouse, but you can rotate it, and it's in a plane. We want to model this whole thing. Okay, we want to make a model of this. Actually, we're going to do it two ways. I'm going to do it first with the equivalent one-dimensional problem in just a second, but here's the problem that we have. Here's the Earth and the quote moon, I don't know actually what it is, and we have some coordinate system. Now, if I want to represent the Earth or the planet with a vector, I can call that R1, and that's a vector. Then I have to also represent the other object, the moon, with a vector R2. Well, this is in three dimensions, so R1 has three coordinates, x1, y1, z1, and R2 has three coordinates, x2, y2, z2. So we have 6 degrees of freedom. If you want to fully describe where everything is in the system, you need 6 variables, and these are the 6 variables that you would need in Cartesian coordinates. So it's not a trivial problem. I mean, 6 degrees of freedom, and we're going to reduce that. That's the key. We're going to use some tricks to get this down. So the first thing we're going to do is define a couple of things. If I have my two objects right here, I'm going to define this vector R, which is the vector from, I'm going to call it from star 1 or planet 1, whatever you want to call it, object 1 to object 2, and I'm going to call that the vector R. And since it's a vector, I can just write vector R is equal to R2 minus R1. It's a displacement vector, right? If it ends at 2, it starts at 1, then that would be the vector R. I also want to define the vector capital R. This is a vector from the origin, wherever that may be, to the center of mass of the system. And then we can define the center of mass as just a normal center of mass, which is m1r1 plus m2r2 over the total mass, m1r2. So we didn't really do anything here. I still have 6 coordinates, right? R, the vector R, has 3 variables. Capital R has 3 variables. And you can't say capital R. I mean, you can write capital R, but I never thought about that. It's not really good for presentations. Okay, well, let's move on. So I want to write the kinetic energy for the system because I want to use the Lagrangian, which uses kinetic energy and potential energy. So the easiest way is to write the kinetic energy in Cartesian coordinates. So I have 2 masses. Each mass has 3 degrees for x, y, and z. Cartesian coordinates is easy, right? It's 1/2 m1 times the velocity of 1 squared, which is x1 dot. Okay, I guess I should write this here. x1 dot. The notation we use is dot notation. Is instead of writing dx dt, we're going to write x dot, and the dot means derivative with respect to time. A double dot would mean the second derivative with respect to time. It's just a notation that we use. It looks cool, and so when people look at this, they're like, oh, that's crazy complicated. It's got dots, but it's not that bad. So, but I can write that in Cartesian coordinates. It's not too bad because here is the trick, right? I'm not going to go through everything in here, but if I write the vector r1 as x1, y1, z1, I take the derivative, I do get x1 dot, y1 dot, z1 dot. So there's a small trick, and there's some steps here to show you, but this notation that I want to use, and a lot of people use this just not even explaining it, is I'm going to use the vector r1 dot magnitude squared. And it works, okay? You can work out the math. It does work. You could just do the x coordinates, all the x coordinates, and then do all the y coordinates, all the z coordinates, and you can write kinetic energy like this. It's r1 dot squared. Not even explaining it, is I'm going to use the vector r1 dot magnitude squared. And it works, okay? You can work out the math. It does work. You could just do the x coordinates, all the x coordinates, and then do all the y coordinates, all the z coordinates, and you can write kinetic energy like this. It's r1 dot squared, 1/2 m. Oops, that's a mistake. That's 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared. I'm not going to fix it. I think you guys can see that that's a mistake, and I've already started, and I can't go back. I can't go back now. So if I have the center of mass vector, r, capital R, we already saw that, and I have the definition of the displacement vector from object 1 to 2, then I can use both of these to get expressions for r1 and r2 in terms of r and capital R. So I can just rewrite the vector r for the center mass. This just separates the two into two different fractions. And then I can solve for r2 for my other equation and substitute that in to the center mass equation. So I haven't done anything here except substitute. Instead of r2, I put r plus r1. Now I can just, what did I do here? I multiply, I get the r1 terms together, I get the r terms together, and you get this. And you can see m1 plus m2 over m is 1, and then I get m2 over m. So this is an important equation. And in this whole presentation, important things get a box. So this has a box around it. So the vector r1, in terms of the center mass, and the vector from one to the other, is capital R. R the center mass vector minus m2, the mass of the other object divided by the total mass times the vector from mass 1 to mass 2. And you could redo this for the other object, and you could get, it's not hard, you can get this for r2, depends on the center mass vector r plus m1 over m times the vector r. Okay, so now I want to rewrite the kinetic energy in terms of not r1 and r2, but the center mass r and the displacement r. So I start right here with my r1 vector, which I just found. And if I want to take the derivative of that, if I take the derivative of r1, because I need the velocity, I'd have to take the derivative of the other side too. So the derivative of capital R is pretty easy to do, right? I can do that. That's going to be just, oh yeah, so here's my kinetic energy, but I want to take the derivative. I think I put this out of order. So r1 dot vector, that's just the derivative of the center mass position, and then m2 over m is a constant scalar, so then I get the derivative of r. So I can put r1 dot into my kinetic energy equation, and then I can do the same thing for r2 dot. I now know the expressions for those. So if I put those in for r1 dot squared and r2 dot squared, I get this. Okay, and now you notice something. I said I'm tired of writing vectors over dots because it's just kind of silly. So here, this is a shortcut notation. R dot here is a vector. Okay, but I'm squaring it eventually, so it's going to end up as a scalar. So technically there should be a vector over there. Both of those r dots should have, there's a three-dimensional thing, so those are not scalar. I start right and get this for r2, depends on the center mass vector r plus m1 over m times the vector r. Okay, so now I want to rewrite the kinetic energy in terms of not r1 and r2, but the center mass r and the displacement r. So I start right here with my r1 vector, which I just found. And if I want to take the derivative of that, if I take the derivative of r1, because I need the velocity, I'd have to take the derivative of the other side too. So the derivative of capital R is pretty easy to do, right? I can do that. That's going to be just, oh yeah, so here's my kinetic energy, but I want to take the derivative. I think I put this out of order. So r1 dot vector, that's just the derivative of the center mass position, and then m2 over m is a constant scalar, so then I get the derivative of r. So I can put r1 dot into my kinetic energy equation, and then I can do the same thing for r2 dot. I now know the expressions for those. So if I put those in for r1 dot squared and r2 dot squared, I get this. Okay, and now you notice something. I said I'm tired of writing vectors over dots because it's just kind of silly. So here, this is a shortcut notation. R dot here is a vector. Okay, but I'm squaring it eventually, so it's going to end up as a scalar. So technically there should be a vector over there. Both of those r dots should have, there's a three-dimensional thing, so those are not scalars. But I can do this. I can work with this. So let's multiply out. This is the kinetic energy equation. Now I'm just going to multiply out the squares, and I get this. So I multiply out that first one. I'm going to get, I left the 1/2 out front. I get m1 r dot squared. Then the other term is I'm going to get m2 squared over m squared r2 dot squared. And then the cross term is going to be negative 2 m1 m2 over m. Yeah, I don't even want to read that. And then I can do the same thing for the other term. And I'm going to get some stuff that cancels. In particular, those two terms cancel because one's negative and one's positive. Yay for us. And if I factor out the capital R terms and the lowercase r dot terms, I get this as a kinetic energy. So for the capital R, I have m1 plus m2. That's just the total mass. And the other one, I have m1 plus m2 as the total mass, and that's going to cancel with one of the other masses. So that for the r term, the lowercase r term, I have this m1, m2 over m, and we are going to call that the reduced mass. This is super important, and I didn't even put a box around it. Okay, but this is super important because this reduced mass shows up a lot going on forward. Okay, and I'm going to tell you what it means. But now I can write the kinetic energy as 1/2 total mass times center mass velocity squared plus 1/2 mu, the reduced mass, times the displacement vector from mass 1 to mass 2 velocity squared. Okay, so it's kind of a big deal. See, it's a big deal. There's a box around it. So that means that I can take this situation. Here are two objects interacting gravitationally, and then the white thing is the center mass. So it's moving at a constant center mass velocity, but it's a complicated thing. I can break that into this, a motion about the center mass plus a motion of the center mass. So it's two separate things. So I can represent the motion about the center mass with this kinetic energy 1/2 mu r dot squared. And remember, r is still 3 dimensions. Okay, and then the center mass is 1/2 m r center mass dot squared. So I can separate that. Right? I have two different kinetic energies. It's kind of a big deal. Okay, now let's go over to use this for Lagrangian mechanics. So if I want to write down the Lagrangian, I'm going to link my introduction to Lagrangian mechanics down below because I can't go over that whole thing right now. But the idea is to take the kinetic energy T minus the potential U. And so if I write that for my central force problem, any central force problem, I have 1/2 m total mass times the velocity of the center mass squared plus 1/2 reduced mass times the relative velocity squared. And then I have the potential term, which only depends on the relative position. Lowercase r does not depend on the big R. That's a big deal. Okay. And once you get a Lagrangian, then you can use the Euler-Lagrange equation to find the equations of motion. This in general says if I have variables q and q dot, so there could be many of them, right? And in this case I have six variables. Then the partial derivative of the Lagrangian with respect to q, one of the q's, is equal to the derivative with respect to time of the partial of L with respect to the velocity. I know that's complicated. So, but let's look at that for the for one of the variables. So one of the variables in here, I have 6 variables, right? I have Rx, Ry, Rz, and then I have the lowercase Rx, Ry, Rz. That's 6. If I take the partial of that Lagrangian with respect to the x component of the center of mass, I get 0. Because the only variable in there, I have Rx dot, I have Ry dot, I have Rz dot. But I don't have any capital R's. The potential doesn't have an R. So I get 0. 6. If I take the partial of that Lagrangian with respect to the x component of the center of mass, I get 0. Because the only variable in there, I have Rx dot, I have Ry dot, I have Rz dot. But I don't have any capital R's. The potential doesn't have an R. So I get 0. That means that if I take the derivative of the Lagrangian with respect to Rx dot, then I can take the partial of that, but then when I take the derivative of it, it has to be 0. So the partial with respect to Rx dot is just going to be, I bring that to power rule, I bring the 2 down, the 2 over 2 is just 1, so I get capital M R dot. And that has to be a constant, right? It has to be equal to a constant because the derivative of that is 0. The time derivative of that is 0. I can redo the same thing for the y and z components, and it looks exactly the same, so those have to be constant. So I can write this, the center mass velocity has to be a constant. And if it has to be a constant, I'm going to pick that constant to be 0. Why the heck not, right? Make it easy for myself. So if that's the case, if the velocity is constant and 0, then I have a much simpler Lagrangian. It looks like this. I have 1/2 mu r dot squared minus ur. And if you go back up here, that first Lagrangian has 6 degrees of freedom. That has 3. So we have just taken the problem from 6 coordinates down to 3 coordinates. That's kind of a big deal. And we're going to keep going. Okay. But what we did was basically separate it from a center mass and reduced mass, relative mass problem, and then say the center mass is at rest. If the center mass is not actually at rest, we can always just add that in later. Okay. Okay, so let's look at the center of mass system. If we already said this, the velocity of the center mass is 0. I'm going to also say that put the origin at the center of mass, because I'm going to make things as easy as possible. So here's my new system. I have mass m1 and mass m2, and the x represents the center mass at the origin. So now I have vector r1 is from the center mass and from the origin to mass 1, and then r2 is the vector to mass 2, and this is the vector from mass 1 to mass 2. But that makes my other equations relating the relative positions to the absolute positions pretty easy, since r is 0, the capital R is 0. So I get these two equations. And now I can use these two to reduce this to even fewer degrees of freedom. And we're going to use angular momentum to reduce this to the next step. And we do have a problem here that angular momentum is traditionally represented by the vector L. L is r cross p, where p is the momentum. And so this is not the Lagrangian. This is the angular momentum. I know that stinks. I don't know any way to fix that problem except to build a time machine, go back in time, and have people choose different variables for this. But we're grown-ups, we can handle it, right? So that's the definition of angular momentum. So for this system, the angular momentum is the angular momentum of star 1 plus the angular momentum of star 2. So it's r1 cross p1 plus r2 cross p2, and that is the cross product. And then I know p1 is the velocity times the mass. So it's r1 dot times m1, and I can factor that m1 out front. So I get this expression for m1 r1 cross r1 dot, which is still 3 dimensions, plus m2 r2 cross r2 dot. Now I can use my relative, I want to get these in terms of the relative vector r, because I want to go back to 3 degrees of freedom. So these are my two relative velocity, relative position vectors. I take the derivatives, I get this, which is pretty obvious. It's in 3 dimensions, but I think it's okay. So R1 dot, I can get that in terms of R dot. Now, the relative vector arcs, I want to go back to 3 degrees of freedom. So I get this expression for m1 r1 cross r1 dot, which is still 3 dimensions, plus m2 r2 cross r2 dot. Now I can use my relative, I want to get these in terms of the relative vector arcs. I want to go back to 3 degrees of freedom. So these are my two relative relative position vectors. If I take the derivatives, I get this, which is pretty obvious. It's in 3 dimensions, but I think it's okay. So R1 dot, I can get that in terms of R dot. Now if I put that into my angular momentum, I get the following. So here I have the mass 1, I get m2 over the total mass 2 term, and then I get r cross r. R dot. Another one also has R cross R dot, and it has m1 squared over m total squared. So I can factor those out, and I get the following. I get m1 plus m2 over m's total mass squared, and yes, one of those cancels, and then I'm left with m1, m2.
start our discussion by the study of what are known as central forces. So first let me define a central force. A central force has some very important characteristics. It is a type of force which always points radially, and the magnitude of the force depends only on the distance from the whatever is the source. Let's take an example right away. Imagine that you have a let's talk about a three-dimensional situation. Let's say I have these the coordinates x, y, z, and let us say that I have a some heavy mass, which is, let's assume that this mass is so heavy that it is not moving appreciably due to another small mass, which is m. So this will satisfy these two conditions. That first of all, it is radial because it is always pointing along towards the origin, or assuming that this mass capital M doesn't move appreciably. If it did, then also, as we will see later on in this in these lectures, that you could always define an this reduced mass by which you could say that the force is always acting towards towards that reduced mass. So anyway, what we're saying is that, you see, the first thing is to understand that this is acting radially, meaning that if you consider some origin, okay, that force is always either towards or away from that origin, which is exemplified by the gravitational force. Or you could also consider the electrostatic force between two charges, and that electrostatic force will also be, assuming that one particle is stationary, that will also be radial, and its magnitude both for the electrostatic and for the gravitational case. This is also true that the magnitude will depend only on the distance from the source. That follows from either Newton's law or Coulomb's law, whatever you have. So another important example. So we listed three types of forces that can be classified as a central force. One of them is gravitation. You could also have spring forces. They also point along one particular direction, so that's also a central force. And also, as I said, that you could have, say, electrostatics as some examples of central forces. Okay. And the reason we study this is obvious. That is when the forces that I have listed over here, these are some of the most important forces in nature. And also, for example, if you want to study the the rotation of a planet about the sun or something, to a very good approximation, you could ignore the effects of the other planets and consider this only as a two-body system in which my definition of the central force will hold. Now, why are central forces so interesting? Let me start off with an important result. That suppose a particle is moving under the influence of a central force. So we will consider a particle of mass m moving under the influence of a central force. And if you consider the angular momentum is r cross p. So if you were in this example, the r would be over here, and p can be, the velocity can be in any direction. Like as in, the force is acting in this direction, but it really need not be that the particle is just coming and falling on each other, because they might have some initial speed or something because of which it might be moving in some arbitrary direction. Doesn't matter. But angular momentum being r cross p implies that if you take dl upon dt, the derivative of the angular momentum with respect to time, then you'll have dr dt cross p plus r cross dp upon dt. Now look at this expression very carefully. See, dr dt is what you call as a velocity. And what is p? P is mass times the same velocity. And what is dp dt? dp dt is just f. And as I said, that because the central force is always radial, f is always along r. Therefore, both these terms are 0, and therefore the total result is 0 plus 0 equal to 0. So in writing this, what I have assumed is that it is now good to write the central force explicitly. You could write this as f as a function of r. That should be the vector sign over here. F as a function of r is the magnitude f times r cap. Well, you've learned about the the radial plane polar coordinate. So that is, in that sense, I'm talking about this r cap. Okay. So what we've shown, over here, if you now come back to this expression, so this is r cross f r cap, and that is obviously equal to 0. Right. You could also write this. Fr. You could, in terms of the potential, you could also write this as minus dv dr r cap. Now note that I immediately have a very important and interesting result, which is namely that when a particle undergoes a central force, its angular momentum is conserved. That is, dl dt is equal to 0. What does that mean? Well, first of all, of course, you know that angular momentum being conserved, you see, the angular momentum vector is conserved. So the angular momentum vector being conserved means a very important thing, that for a particle moving under the influence of a central force, okay, the motion must always be on a plane. Notice the very, very important thing that we have obtained over here, that we have said that the motion must always be on a plane. Now, this plane, and okay, first of all, why is that? That is because, you see, the angular momentum is conserved means the direction as well as the magnitude of the angular momentum is conserved. So if the particle is, let's take a fiducial plane like this over here, and the particle is moving under central force on this plane. Say this is the origin O, and the particle is moving over here like this. So your r cross p would be pointing vertically, or rather pointing perpendicular to that plane. Now, if the particle left the plane, if the particle is now not moving on the plane, obviously its direction of angular momentum will change, but that is ruled out just as we saw over here. the particle has can always be described as planar motion. And the moment we realize this fact, we have really simplified the problem, because you know that planar motion can always be described by means of plane polar coordinates. So here you know that planar motion is always described by plane polar coordinates, and I will give you a brief review of that just now in a little while. But we will, I mean, if you have forgotten, or rather if you are not confident about the radial polar coordinates, please do the plane polar coordinates, please do brush up, because that will be very, very important for these discussions. So remember that the particle need not be on a horizontal plane. That's what I want to emphasize. I mean, it can be moving in some other tilted plane type of thing. I mean, the plane in which the particle moves can be tilted with respect to the horizontal like this. It doesn't really matter. But the motion is always on a plane, and because the motion is on a plane, you only need two coordinates to describe the motion. So therefore, what we have established is that, although I mean I did not make any assumption about motion in 2 dimensions. Remember when I said I drew this coordinate axis, which is a proper 3-dimensional thing, and there was a particle moving on that. But what we see is that by definition, just from the fact that the angular momentum is conserved, as we showed over here, the motion must be on a plane, and a plane needs only 2 coordinates. So therefore, you have now effectively reduced the problem from a 3-dimensional system to a 2-dimensional system. Okay, so that is the first simplification. But that's not all. We will see that there is another huge simplification will come. Okay, and let us therefore take the next step. Now, I would just for 2 minutes, just to brush up, I will give you the broad overview of these plane polar coordinates, because it is going to be so important for us. And you know the plane polar coordinates you've already studied in the first part of this course. You have these x, y, which are the usual Cartesian coordinates, and plane polar means what? Means this r theta. If a particle is over here, then you could describe it by 2 Cartesian coordinates x and y, or you could describe it by 2 coordinates r and theta, and the relation is x equal to r cos theta, y equal to r sin theta. So those things you know. But all that I wanted to remind you is that if you write the vector r in terms of the polar unit vectors, what are the polar unit vectors? These are r cap and theta cap. So remember that r cap points along r, and theta cap conventionally is taken to be pointing perpendicular to r cap in the anti-clockwise direction. And if that is the case, then remember that this implied that the velocity of the particle will now be r dot r cap plus r cap dot. And by a dot, I always mean a derivative with respect to time. That is, this dot implies is equivalent to d upon dt. So this was the expression for the velocity. The velocity, because r dot is dr dt is the velocity. But then you also would remember, if you don't, please go and brush up. So r dot cap was theta dot theta cap, and theta dot cap was equal to minus theta dot r cap. Okay, and once you do that, once you take that expression, because you see, if you look at this expression, this is not very useful because it contains this one. Okay, r cap dot. But I could as well write this as, this is r dot r cap plus r theta dot theta cap. And this is basically the well-known expression for the speed, or rather for the velocity v in plane polar coordinates. So this is like equal to the velocity v in plane polar coordinates. And similarly, if you, I mean, this I did not get into the derivation. It's rather simple. If you, for example, if you calculated what is not a very good color, if you calculated what is r double dot, just again by following the same logic, you would probably remember that formula, it came out to be r double dot minus r theta dot squared into r cap plus r theta double dot plus twice r dot theta dot into theta cap. And if you multiply it by m, then you will get the force. But now look, what I will do is I will multiply this by m. Puts an m over here. Puts an m over here. But now if you go back and look at what I have written over here, the central force is a force which only depends on r cap. That's how I defined it. Therefore, from this expression, from the last expression over here, which is a general expression for the force in 2 dimensions, if I specialize to the case of a central force, then this term will not be there, because central force, I said, it can only depend on r cap. Therefore, this the central force is F, is m mass into acceleration. This is equal to m r double dot minus m r theta dot squared times r cap. Okay. And now, if you also remember, I had used another expression which is over here, that F is minus dv dr r cap. So therefore, I write over here minus dv over dr, and this is r cap, and this r cap also occurs over here, so I can only consider the magnitude because only the r cap direction occurs. So minus dv dr, therefore, must be equal to the force which I've already written down, mr. sorry, this is mr. Therefore, only the r cap direction also occurs over here, so I can only consider the magnitude because only the r cap direction occurs. So minus dv dr, therefore, must be equal to the force which I've already written down, mr. sorry, this is therefore, and my another expression which is over here, that F is minus dv dr r cap. So therefore, I write over here minus dv over dr, and this is r cap, and this r cap also occurs over here, so I can only consider the magnitude because only the r cap direction occurs. So minus dv dr, therefore, must be equal to the force which I've already written down, mr. sorry, this is so this is mr theta dot squared. This is an identity, and therefore I come up with an important relation that mr double dot, that is equal to mr theta dot squared minus dv by dr, and this is the first equation that the dynamical equation that we derive for central forces. What is the left hand side? The left hand side is, this is basically the force equation, right? I mean, of course, you cannot call the left hand side as the mass as the mass into acceleration, because obviously the acceleration is both in the radial and in the tangential direction, and the acceleration is equal to the radial acceleration is r double dot minus r theta dot square. So r double dot is not the radial acceleration really. But this is the dynamical equation, the first dynamical equation that we derive. Okay, dynamical equation, the first dynamical equation that we derive. So this is the dynamical equation, the first dynamical equation that we derive. Okay. Now, if you let me just continue the story. I will also write down the equation for the angular momentum. So angular momentum is r cross p, which is r cross mv. Mass is a constant, so I've taken the mass outside. Okay, and this I can now write as m into, this is r cap cross. I've already derived the expression for the velocity over here. So this is cross r dot r cap plus r theta dot theta cap, right? And if you take the cross product, and obviously the r cap cross r cap, that is the first term, will go away, and the second term is now m. Okay, the second term is, remember, this is r cross r theta dot theta cap. So this is m r squared into theta dot times, I will just write this as some n cap. Well, n cap is, this is r cap cross theta cap. So whatever plane that the motion is taking place in, n cap is actually points out of that plane. Like this. So in any case, what we therefore obtain is that the magnitude of the angular momentum is given by m r squared theta dot. And remember, very importantly, we had said that the angular momentum is a constant, and therefore, I mean, now so this also implies that, please just take a look of what I'm writing. L squared by m r cubed is what? This is equal to m squared r to the power 4 theta dot squared by m r cubed, which is equal to m r theta dot squared. So therefore, I can just put this fact in this equation and write this as m r double dot. I just showed you that m r theta dot squared is L squared by m r cubed. So let me just quickly substitute that. So this is like L squared by m r cubed. Please just take a look of what I'm writing. L squared by m r cubed is what? This is equal to m squared r to the power 4 theta dot squared by m r cubed, which is equal to m r theta dot squared. So therefore, I can just put this fact in this equation and write this as m r double dot. I just showed you that m r theta dot squared is L squared by m r cubed. So let me just quickly substitute that. So this is like L squared by m r cubed minus dv by dr. And what have I achieved by writing this? Well, I've achieved something quite miraculous, actually. Miraculous, I mean, quite remarkable. Which is namely that, you see that all the dependence on theta has gone away, right? Because you see, left hand side mein you have m r double dot, wo to sirf r ke upar they will depend on r. Right hand side mein L is a constant, don't worry about it. Mass is also a constant, you all have r. And as I said, the potential, now you see, because I wrote the central force like Fr is minus dv dr and r cap. And because the force by definition depended only on the magnitude of the distance, therefore I can just write this v. This potential must also only be a function of the distance, otherwise the definition of the central force will not work. Okay. So if v is only a function of r, only then will the derivative, that is the force, be a function of be dependent only on the distance. No. So that is why the potential also has to be only a function of the distance from the origin. So therefore, this dv dr is also a function only of r. And therefore, what you have achieved over here is that now this has effectively become a one-dimensional problem with that one direction being r. Okay. So therefore, you started with a three-dimensional situation. Now, from the fact that the angular momentum is conserved, we made it into a two-dimensional problem. Now, from the fact that the magnitude, so that was actually from the fact that the direction of the angular momentum is conserved, because remember that the angular momentum as a vector was conserved. Now, from the fact that the magnitude of the angular momentum vector is conserved, I could write that, I could write this theta dot squared over here in terms of L squared by m r cubed, where L is the magnitude of the angular momentum, and from the fact that this is L is a constant, it's a conserved quantity. So therefore, I could write theta dot squared entirely in terms of r, and therefore, you see that here in this equation there is no explicit theta dependence. Of course, you might say here theta is there, no? Well, it is there, but it's there as theta dot squared, which is precisely, as in theta dot or theta dot square, which is precisely related to the angular momentum by this relation. So whenever you see a theta dot, you could replace it by L by m r squared, and because L is a constant, it's great. I mean, we do not have any theta left in this problem. Okay, so therefore, what I've shown you now is that what this tells you is that the problem has now reduced to a one-dimensional problem, and that one-dimensional as if you have one variable, and that one variable is R. Great. So now, what else? What can we do over here? We can do something much more. So now, if you look at this relation, okay, I'm going to write this in a slightly different way. I mean, not different. I'm only going to multiply this out by an R dot. So this I write as L squared by M R cubed R dot minus R dot into dV upon dr. And this equation I could write, just look at what I'm doing. So this is M by 2 d upon dt of R dot squared. Obviously, that's the left hand side, obviously, because ddt of R dot squared is 2 R dot R double dot. वो दो factor जो है वो वहां से cancel हो गए, and this is therefore the exact expression for the left hand side. Fantastic. The right hand side, what should I do? I should write this as minus ddt. Remember, L is a constant. Minus ddt of L squared by twice M R squared, because इसका derivative करो. L is a constant, M is a constant. So ddt of minus ddt of 1 over R squared is 2 by R cubed, rather, because of the minus sign will go away from here. So this will give you basically this term, which is like L squared by M R cubed into R. And this I can write as again as minus d by dt of V of R. As squared here. dt, because by twice constant, minus ddt of L squared by twice M R squared, because इसका derivative करो. L is a constant, M is a constant. So ddt of minus ddt of 1 over R squared is 2 by R cubed, rather. Because of the minus sign will go away from here. So this will give you basically this term, which is like L squared by M R cubed into R. And this I can write as again as minus d by dt of V of R. Wonderful. So therefore, what I can do now is I can take all these terms to the left hand side, dt of V of R. Wonderful. So therefore, what I can do now is I can take all these terms to the left hand side, and I can write that ddt of half M R dot squared plus L squared by 2 M R squared plus V of R is equal to 0. So the time derivative of this fellow inside the bracket does not change, and that therefore means that half M R dot squared plus L squared by twice M R squared plus V of R must be some constant, and I claim that the constant is simply the total energy. Or you might say, what else is there? I mean, yeah, but don't. There might be some hidden symmetries or whatever. You never know. But I claim that this constant is energy, and why is that? That is because you see, that what is the kinetic energy of the particle? The kinetic energy is half m r dot squared, right? And r dot I have just defined m kinetic energy of the particle. The kinetic energy is half m r dot squared, right? And r dot I have just defined for you is r dot r cap plus r r dot r cap plus r theta dot theta cap. So r dot squared. What is r dot squared? The r dot squared is basically like I mean, as the square of this is r dot squared plus r squared theta dot squared. That's the square of the velocity. So therefore, I go back over here and write this as half m r dot squared. This is half kinetic energy is what I mean is this over here. This is half m r dot squared plus half m r squared theta dot squared. right? It's making sense, right? Because I mean, all I mean is that it's not that there was a vector sign which I forgot to put before. This is just half mv squared. Half mv squared, the velocity का formula तो we had derived before, that is your r dot r का plus r theta dot theta का. इसका square करो तो r dot squared plus r squared theta dot squared. I've just multiplied this by a half m. And now, if you add the potential energy, so that I write as Vr, this should be equal to E. Now note that this term, what is this term? This term is nothing but L squared by twice mr squared. Why? Because L squared by twice mr squared, remember L squared is m squared r to the power 4 theta dot squared, because I just proved that L is equal to mr squared theta dot. This divided by twice mr squared squared over here. This is like mr squared theta dot squared divided by 2. This is precisely this term. And what have I written over here? This is the total energy. Therefore, I would identify this constant, the ddt of whatever had come. I have therefore shown you is nothing but the total energy of the particle. So therefore, I have now an equation. You see, now what is the use of this equation? Well, the use of this equation is that you have a simpler thing to solve, in the sense that, you see, the equation that I wrote over here, that was fine, but now I have used one more conserved quantity. And this is something that you will come across many times, that if there are symmetries in the system, there are conserved quantities. Using those conserved quantities, you can reduce the symmetries in the system. There are conserved quantities. Using those conserved quantities, you can reduce the order of the dynamical equation from a second order differential equation to a first order differential equation. And indeed, if you look at this equation, this is r dot, r double dot doesn't appear over here. So in principle, I could write a formal expression for r dot and solve that equation in order to get my write a formal dot doesn't appear over here. So in principle, this is r dot, r double dot doesn't appear over here. If you look at this equation, this is r dot, r double dot doesn't appear over here. So in principle, I could write a formal expression for r dot and solve that equation in order to get my formal expression for r dot and solve that equation in order to get my stuff. But before we do all the equation, in order to get my formal expression for r dot and solve that equation in order to get my stuff. But before we do all these things, let us just take a fresh look at this equation, which I would write once more, which is namely that we wrote half m r dot squared plus L squared by twice m r squared. Okay, plus v of r, this is equal to E. V of r is equal to E. So if you look at this expression, you see that the first term, I mean, forget about the fact that r is a radial coordinate. Okay, look at the first term. First term looks like half m x dot squared type. Don't think of r as a radial variable. Okay, think of r as some coordinate. Don't think of r as a radial variable. Okay, think of r x dot squared type. Don't think of r as a radial variable. Okay, think of r as some coordinate. Now we have reduced the problem to 1 dimensions. So this is looking like the half mv squared type of thing. Of course, I warn you that this is not the velocity in two dimensions, because that velocity was r dot squared plus r squared theta dot squared. But imagine this like a effective one-dimensional problem where r is a coordinate. Okay, so this is like the kinetic energy effectively, and this guy is what is a very important thing, what is called as the effective potential energy. So it is so important, I will write this once more. V effective is equal to L squared by twice mr squared plus the actual potential energy. So remember, don't make the mistake of thinking of this r dot squared as a full kinetic energy. It is not. Of thinking of this r dot squared as a full kinetic energy. It is not. So remember, don't make the mistake of thinking of this r dot squared as a full kinetic energy. It is not. Which may we have done a lot of things. We have written the theta dot squared term, then we have used what have you, the angular momentum, blah blah blah, all these things. But it is effectively looking like a one-dimensional problem in coordinate r, effectively. But I have an effective potential, which is this. Okay, this is the effective potential. So therefore, I would write the total energy to be equal to half m r dot squared plus v effective. Now, v effective is a function of r, right? Because you have L is a constant, m is a constant, r away, then this is v of r. And if you typically, okay, if you look at this thing, if v of r is a well-behaved potential, then as I go to r nearer to 0, this guy will tend to diverge. And if you, depending on what is your VR, I'm just assuming that VR is maybe some r or something like that. And if you go to r going to infinity, then this term, the effect of this term will vanish. Well, also again depending on what your VR is. But I will draw for you a very typical graph. So this is, I'm drawing r on the y-axis. I have very sorry. So on the y-axis I have v effective of r. Typically, in the situations that we will come across, remember r cannot be negative, so I probably did not draw such a big y-axis. So this is this thing. Typically, you will find that and if you plot it for the problems that we will consider, it goes like this. V effective goes like this. Now, if you, of course, it can also. There's nothing saying that this has to be positive only. There is, it is quite possible that it goes like this. But what I'm saying is that if you now look at this expression for the energy that I've written, the energy must always be the energy. Cannot be less than the minimum value of the V effective. Cannot be less than the minimum value of the V effective. Why? Because if the minimum value of the V effective. Why? Because if ever energy is less than V effective, this side is lower than this, then half m r dot squared will become negative, so r dot will become imaginary, which is not allowed. negative, so r dot will become imaginary, which is not allowed. So therefore, I can have two situations. One is E is equal to V effective, and one is E, which must be greater than. I mean, what I mean that when greater than V effective means the minimum value of V effective. It has to be always greater than. Maybe I just put the whatever is the minimum value of V effective. So that is what I mean. So in the first case, suppose I draw. So let's focus on the graph above. I mean, it can be the graph below also. I draw what is E. You see, this has a one point at which it touches, and we will see that this effectively means that half mr dot squared is 0 because E is equal to V effective. I'm talking about this case now. So half mr dot squared equal to 0. So if E equal to V effective, this implies that r dot is equal to 0. Equal to V effective, this implies that r dot is equal to 0, which means that r is a constant. Now, if you go back to your two-dimensional interpretation, this means that the particle is moving in a circle. This means that the particle is moving dimensional, which means that r is a constant. Now, if you go back to your two-dimensional interpretation, this means that the particle is moving in a circle. And suppose if you have the other situation, that is E is greater than the minimum of the effective potential, then what you would do is again draw the E over here. So this case is E greater than the minimum of the effective potential. And here you see that graphically you get two extreme solutions. Okay, which means that the particle's motion is actually bounded between these 2 points. Call this as r1, call this as r2. Because if you are slightly lower than r1, then say you are at this point, let's say, and let me just extend this graph a little bit. At this point, what will happen is if you just drop a perpendicular over here. Okay, let's say this was, or maybe I'll just draw this figure a little better. So this is my graph. This is your r. This is your V effective. And let me draw it a little. This is my E, and what I'm saying is that this is your r1 and this is your r2. I claim that the particle is confined between this r1 and r2 because suppose if you take a point which is over here, let's say this r, for this particular value, you see that this V effective, okay, is greater than the corresponding energy. And just by the argument that I gave, if V effective is greater than the energy, then r dot will become imaginary. That is what it is. Exactly in the same way, you cannot have a you cannot have a particle at this point. You cannot have the particle at this point. Okay, so because again over here, the effective potential will become greater than the energy, which will make the motion impossible. So therefore, the particle has to be confined between the positions r1 and r2. Okay. Let's continue with the central force topic. So we saw last time that a very important relation that we wrote down was half mr dot squared plus V effective is the total energy, where I also wrote that V effective was defined to be L squared by twice mr squared plus the actual potential. And as I told you last time, this equation on your left, now you should think of it as an effective equation with an effective potential energy plus kinetic energy term, which equals the total energy. And we also talked about how to interpret this in the by drawing the effective potential and by looking at the shape of the effective potential. So now to continue, we have to do some more. I mean, last time I showed you some pretty much numerical, pictorial description of the whole thing. But remember that one needs analytic solutions, and in order to do that, I will write down the other equation that we had, which is mr squared theta dot equal to L, the angular moment. And so this E and this L, these are the two constants. We saw that how the angular momentum is conserved in central force motion. That's something that I proved last time. And of course, the total energy will have to be a constant quantity. So having given these two equations, what you can see is that I can try and do an operation by which I determine what is the shape of the orbit. Now, this is also quite interesting because you see what I told you. Try and do. What you can see is that I can try and do a constant quantity. So having given these two equations, what you can see is that I can try and do an operation by which I determine what is the shape of the orbit. Now, this is also quite interesting because you see what I told you last time is that suppose if you took this equation, then in principle you could write down mr dot squared by 2 is equal to E minus V effective, which means that r dot is 2 by m E minus V effective is square root. And therefore, in principle, once you are given, what is the given an energy, once you're given the effective potential, you could integrate this equation. The right hand side is a function of r, and you could try to integrate this equation and get r as a function of t. Right? But that's not very interesting because having given these constant quantity. So having given these two equations, what you can see is that I can try and do an operation by which I determine what is the shape of the orbit. is also quite interesting because you see what I told you last time is that suppose if you took this equation, then in principle you could write down m r dot squared by 2 is equal to E minus V effective, which means that r dot is 2 by m E minus V effective iska square root. And therefore, in principle, once you are given, once you are given what is the given an energy, once you're given the effective potential, you could integrate this equation. The right hand side is a function of r, and you could try to integrate this equation and get r as a function of t. Right? But that's not very interesting because what we are really interested in is that suppose if you have a central force, okay, what does the orbit look like? How does the orbit? What does the orbit? Pictorially, how does it look like? So in order to see what happens over there, let's take these two equations and let us do the following. What we do is in the second equation, okay, I use the second equation to write because you see this is like d theta dt. So therefore, what I have is dt is equal to m r squared by l d theta, because d theta dt is l by m r squared.
Over m, which is the reduced mass. So I get this r cross r dot times reduced mass. Now, if I use the angular momentum principle, this says that the total torque on the system is equal to the time derivative of the angular momentum, but there's no torque on the system. The only force I have is a central force. So the torque on the system has to be 0, so the derivative of the angular momentum has to be 0. This is a long video, I know. Okay, you might want to slow this down and replay it, or I don't know, but I'm confusing myself with all the L's. I just want you to know. Just letting you know where we are. But the angular momentum has to be constant. Okay, it has to be constant because there's no torque on the system. We can use this to our advantage. So let's say that I have the relative vector r. I pick it to be in the xy plane, so it has no z component. Then I take the derivative to get the velocity, and it has no z component because it's just the derivative of rx is rx dot. The derivative of ry is ry dot. And then I can use my definition of the angular momentum and actually do the cross product. So here I have mu times the one way to do the cross product is to find the determinant of this matrix where the top row is x hat y hat z. And it's 0 times r y dot. So those are 0. And the next term, the y term, is also 0. And the only term that survives is the z term. So I get a z component of angular momentum. So the angular momentum is only in the z direction. And this is important, right? Because it says that if I pick r in the xy plane, then r dot has to be in the xy plane, and the whole thing has to be in the xy plane. So I can just like I chose to have the center of mass at the origin, I can choose to have the motion in the xy plane. So it's in a flat plane, and I can pick that xy plane. And this is kind of a big deal, so I've made a little animation, say 3 to 2. So we've gone from 3 degrees of freedom for r is xyz, and I just say I don't really care about the z because I pick it to be in the xy plane, and I can do that because of angular momentum. So here we have now a two-dimensional object, and I can represent that with, now this is the scalar value r, right? This is polar coordinates, and I can represent it in terms of r and theta. Now, I do have the following relationship. I know y is equal to r sine theta and x is equal to r cosine theta, and that's important because I still have to get the kinetic energy. The kinetic energy is 1/2 reduced mass x dot squared plus y dot squared, and it's not trivial to get that in terms of the polar coordinates. You could just say, I looked up the kinetic energy in polar coordinates and I'm done, and I'm okay with that, but I'm going to show you how to get it. So if I take x as r cosine theta, and I take the derivative of that, I get r dot, I take the derivative of r dot cosine squared theta, r dot squared sine, done anything other than get it in polar coordinates. So let's go back to the Lagrangian, and here again we're using the Lagrangian L, just to be clear, and I can write my Lagrangian L in polar coordinates like this. Let's start with the theta value. I'm going to take the partial of L with respect to theta, and there is no theta term. There's a theta dot, but there's no theta, and the potential only depends on r. So we're cool, right? And if I take the partial with respect to L with respect to theta dot, I can do that. I get, and this is just a partial, right? So the 2 comes down front, I get 1/2 times 2 times mu times r squared times theta dot. That's it. But since the partial of L with respect to theta is 0, the partial of L with respect to theta dot has to be a constant because the derivative of that is equal to 0. So we're going to call that constant lowercase l. And here you see a little bit of insight. Say, hey, we use that L so many times, we shouldn't do capital L anymore. So it's a lowercase l, and it's just equal to the partial of L with respect to theta dot, and box it, right? Because it's important. So there you go. So we're setting this constant, and it does depend on r and theta dot, but this product of r and theta dot is constant. And this is the angular momentum in the z direction. We'll see that. I'll show you that later. Now let's go over the r variable for the Lagrangian. Here's our Lagrangian. Take the partial of L with respect to r, and I get mu times r. Yeah, there's that from that. There's one r in the r squared theta dot squared term. And it's equal to partial L with respect to theta dot, and box it, right? Because it's important. So there you go. So we're setting this constant. It does depend on r and theta dot, but this product of r and theta dot is constant. And this is the angular momentum in the z direction. I'll show you that. Now let's go to the r variable. Here, that first Lagrangian has 6 degrees of freedom. That is 3. So we
ideally, every time, let's say, at regular time interval, you expect, let's say, 0.15 volts, right, at some point of time at regular intervals on this plot. However, it could be converted to 0.15, it could be converted to 0.155, 0.152, and things like that, right? Depends on the resolution and, again, all these factors. How well the potentiometer pot is able to reproduce the motion of that pendulum, right? So if you take the data like this, let's say stop the measurement, then basically this is what we get, right? So we get this oscillatory behavior. However, I mean, there are these, for example, it's more visible at the peak values. You will see this kind of jittery things, right? Because another thing that is involved here now is, so whenever you digitize something, right, another factor that comes into picture is the measurement time period, right? So this 4096, this 12 bit, right, it converts and all that, at what rate it's going, right? So anyway, so you get this kind of, these multiple points, which are overall, which are representing that trend, right? But otherwise, there could be different individual fluctuations while you measure the same point again and again and again, right? For example, this peak, the central peak in all these parts is supposed to give the exact same value, other than a decrement in the amplitude because of friction and all that, right? However, not every time you will get the exact same value, right? Because I mean, you have 1 millivolt procedure, right? So there could be a few sort of points in there. So, yeah.
Sir, is this smoothing algorithm something like fitting the curve? So there are certain points which do not, in the very shorter range, if you focus on the peak, say.
That you should take. Now you can do point setting the average. Are you going to miss out
Good morning, everyone. Myself, Deepak Dhanova, athletic coach.
Myself, Ratanlal Dhiman, senior PTI. We are going to discuss today on the topic speed, motor ability for sports performance.
Speed. Speed is the ability to achieve high velocity or explosive force applied to a specific task. Speed also involves acceleration, deceleration, redirection, and moving through distance in the shortest possible time. In other words, we can say maximum distance covered in minimum possible time, also called speed. Speed depends on two components: stride length. Stride length depend on your limbs. Turnover speed. Turnover depend on how stride frequently you can.
Now we will discuss energy system for speed. Anaerobic electric pathway, supplied energy for absolute speed. The anaerobic means without or lack of oxygen. Electric mean without lactate. Energy system is best challenged as an athlete approaches top speed between 30 to 60 meter while running at maximum speed. This speed component of anaerobic metabolism lasts for approximately 6 to 9 seconds and should be trained when no muscle fatigue is present.
Types of speed. There are 5 types of speed. 1. Reaction ability. 2nd. Movement speed. 3rd. Acceleration ability. 4th. Locomotive ability. 5th. Speed endurance.
Reaction ability. In sports, reaction ability is required to react quickly and effectively to various signals. Reaction time is most commonly taken as a measure of reaction ability. It must be considered that reaction time does not include the reaction itself. It is the time interval between the signal and the start of the movement. In sports, except in a few events like 100-meter starts, reaction ability cannot be judged simply by considering the reaction time. The speed and correctness of the reaction also has to be considered. But if other things are constant, then reaction time assume high performance for the judgment of reaction ability. A. Time taken by the signal to reach the sense organ. B. Time taken by the sense organ to generate a nerve impulse. C. Time taken by the nerve impulses to reach the concerned centers in the CNS. D. Time taken by CNS to generate a motor nerve impulse. E. Time taken by the motor nerve impulse to reach the muscle. F. Time taken by the muscles to begin the concentrations. Simple reaction ability. In simple reaction ability, the signal and response are both known to the sportsman, that is sprint start. Simple reaction ability is of the importance in start in swimming, cycling, and track and field sprint events. In these sports, the sportsman learns the reaction of movement as a skill, and therefore reaction time is a reliable measure of simple reaction ability. A. Women have longer reaction time as compared to men. B. In track and field, reaction time increases with the distance to be run. C. Elite sprinters have an average reaction time of about 0.12 seconds. D. Reaction time of different body parts is different. Arms are faster than legs and hands are faster than the arms. E. Good sprinters are stable in reaction time performance. F. Reactions are slower if the movement to be exhausted is complex or unlearned. G. Emotions, especially anger, fear, have an inverted U relationship with reaction time. The methods for improvement of simple reaction abilities are given below. A. Journal method. B. Reacting repeatedly on a signal. C. Part method. D. Sensory method. Complex reaction ability. Complex reaction ability is needed when there is uncertainty about the signal or response or both. A. Anticipation. 1. Movement structure. 2. Tactical patterns. 3. Experience. B. Selection of correct response. You can see in the picture below for 4 different stages of 100-meter start, which how a athlete react on the command. Now we will discuss the drills for the development of reaction time. In the following drills are the initial stages of the athlete, and the athlete will react quickly on the different types of the command, like at a gunshot, clap, whistles, go, or start. Athlete will try to acquire maximum speed. Reaction time should be recorded each time, and compare to know the improvement. Drills like simple sitting position, lying face down, lying on their backs, kneeling position, push-up position, sit-up position, standing backward face, different starting position, and many more drill also can be used.
Movement speed. It's the ability to do single movement in minimum time. It is high relevance in acyclic sports, where it is important in the initial phase, like start movement, or some phase in cyclic activity like hurdle clearance or turn in swimming. It's depend on quick contraction of a muscle or a chain of muscles. A single course of movement like jumping, throwing, kicking, etc. is depend to a great extent on explosive strength and technique. Movement speed. Movement speed is of importance in acyclic events and sports. Example throws, gymnastics, and combat sports. In these sports, the movement speed is very closely linked with technique and tactic of the sports. Depending upon the nature of speed, it's further depend heavily on explosive strength, flexibility, coordinative ability, attention. It is movement speed is most frequently improved indirectly by improving technique, explosive strength, and other determined factors. This indirect method has improved to be very effective, but sometimes, especially during the competition period, the movement speed has to be improved directly, and for this purpose, the specific movement is practiced in the following three manners. First, repeating the movement with maximum speed. The concerned movement is executed again and again with maximum speed. It is important to take the time taken to complete the movement as feedback is very important for improving movement speed. In some sports is concerned, movement can be done several times without pause. Example in boxing. In such case, the time of total repetitions should be taken. Practice the movements under easier conditions. The movement is executed at maximum possible speed under conditions which enable higher speed. For example, this can be achieved in the following manners: by reducing the resistance in short put, by doing the movement on a faster surface, by using external help. Example, use board in jump. C or third point, practicing with a faster rhythm. Each movement has its own rhythm. If during the movement execution a slightly faster rhythm is given from outside, the sportsman is able to do the movement faster. Acceleration ability. Acceleration ability, like all other speed abilities, can be improved directly or indirectly. It is improved indirectly by improving explosive strength, technique, flexibility, etc. For the direct improvement of acceleration ability, short sprints are the best means. The distance or duration of these sprints is based on practical experience as well as on some research findings. According to Henry, 1952, found that sprinters achieve their maximum speed in about 6 seconds after the stationary start. Also found that irrespective of the performance level and age of maximum speed is achieved in 5 to 6 seconds after the start. They also found that during a sprint, the increase in speed is as follows. At the end of first second, athlete achieve 55%, second second, 76%, third second, 91%, fourth second, 95%, and at the end of fifth second, 99%, according to Harare, 1986. However, it states that the duration of achieving maximum speed is lesser in case of lower sprinters. In 80-meter sprint, men achieve maximum speed at about 45 meter, whereas women achieve it at about 25 meter. For improving acceleration ability, the following load parameters are suggested: intensity, maximum or near maximum. Duration, the duration of the sprint should be from 4 to 6 seconds. It can be less for children. Distance, in view of duration, the distance will be differ from activity to activity. It will also depend on the nature of sports. Repetition. According to the training state, this should be arranged in series of 3 to 5 or 3 to 5 repetitions. The sprints should be stopped when the time of sprints start decreasing. Recovery. Full recovery in between the series. Duration of recovery will be depend on the duration or distance of sprints. Achieve recovery is advisable in case of long recovery periods exceeding 5 minutes. Methods for acceleration ability: weighted sledge, resistance run, parachute run. The detailed explanation of these points will be discussed in coming slides.
Training for acceleration. Weighted sledge will help improve the athlete's acceleration phase. Parachute run also help in acceleration training. Using a sledge, a light weight of approximately 10 to 15% of body weight should be used so that the dynamics of the acceleration technique are not negatively affected. Start over 10 to 20 meters, performed on a slight incline of around 5 degrees, have an important conditioning effect on the calf, thigh, and hip muscles. For example, they have to work harder because of the incline to produce movement. that will improve sprint acceleration. Now we will discuss locomotor ability. It is the ability to maintain maximum speed of locomotion over as long distance as possible for maximum possible duration. It is important for 100-meter and 200-meter in athletics. Also important in speed skating and short sprints in track cycling. High movement frequency depends to a great extent on mobility of nervous system.
Methods for locomotor ability. Downhill. Downhill sprinting is a method to developing sprinting speed following the acceleration phase. Maximum of a 15 decline is more suitable for hill training. Use 40 to 60 meters to build up to full speed and then 30 meters for maintain the speed or locomotor speed. In this method, difficulty is to find a suitable hill with a safe surface. Overspeed. Overspeed work could be carried out when there are prevailing strong winds. Run with the wind behind you. Sprinting speed. Differential racing with different distance or different pace. Ins and outs. Acceleration run.
This phase of maintenance of maximum speed is different for different person depending on their age and performance level. 12 to 13-year-old children 15 to 20 meter, 14 to 16-year-old children 20 to 30 meter, 12 to 13-year-old trained children 20 to 30 meter, well-trained adults 30 meter and longer. For the improvement of locomotor ability, sprints are used, but the duration distance of the sprint must allow for full acceleration, followed by desirable duration oblique distance of maintenance for maximum speed. The following load parameters are suggested for the improvement of locomotor ability. Intensity, maximum or near maximum, duration 6 to 9 seconds, distance will differ from sport to sport according to the suggested duration of sprint. Repetitions 5 to 10. In case the distance are shorter, these can be arranged in series of 2 to 3 repetitions. Training should be stopped when the sportsman starts getting tired. Recovery, full recovery nature of recovery should be active in case recovery period is longer than 5 minutes. Then a short warm-up is required for the start of next repetitions or series. The locomotor ability depends heavily on the mobility of the CNS and on the ability of the sportsman to relax his non-involved body parts and muscles during the phase of maximum speed. Hence, sprints for locomotor ability must be done with conscious effort to achieve relaxation during the sprint.
Now we will discuss speed endurance. Speed endurance is defined as the ability to perform motor movements with high speed under condition of fatigue. It is a combination of speed and endurance abilities. Continue movement with high speed in spite of the rapid accumulation of fatigue during the activity required for cyclic sports. Again and again with the maximum speed under condition of fatigue. In non-cyclic sports like football, repeated sprints. Speed endurance depend upon anaerobic capacity, psyche, factor and level of skills. Now we will discuss methods for speed endurance. First of all, we will discuss repetition method. This method, when used with specific movements, can be highly effective for improving speed endurance, but for this success, a good level of basic endurance is a necessary prerequisite. Harare 1986 suggests two variations of this method with which can be effective for cyclic sports. Repetition with high speed over distance, which are 2 or 3 to double of competition distance. Example, tempo run up to 300 meter in track and field. Repetitions with maximum speed over distances which are 10 to 20% longer than competition distance. In the above mentioned two variations, required number of repetitions are done with complete recovery in between the repetitions. When the repetitions are done by maximal or near maximal speed, then considerably long recovery periods are needed. But if the speed is low, then shorter recovery periods are needed and repetitions can be arranged in series of 2 to 4 repetitions. Next one, intensive interval method. This method is more suitable for improvement of speed endurance in team games, combat sports and racket sports. In this method, cyclic movements like running, cycling, etc. can be used or specific movements of a sports can be used. The exercise is done at maximum or near maximum speed for a short distance or duration, after which there is incomplete recovery of short duration. The load and recovery phase can also be determined according to the typical competition load structure of a sports. A typical example for speed endurance for hockey and football involving running is given. below an example. Like in hockey and football, speed endurance, intensity very high to maximum, distance 30 to 40 meter, repetitions 3-4 series of 4-5 repetitions. In 4-5 repetition, repeated 3 or 4 times. Recovery 20 to 30 seconds between repetition and 3 to 5 between sets or series. In combat sports like wrestling, boxing, and judo, special circuits of 4 to 8 special exercises can be made and done according to intensive interval method for the improvement of speed endurance. The factors determining speed. Speed abilities are trainable to a very limited extent due to its marked dependence on the functioning of the central nervous system. In practice, therefore, speed performance are commonly improved not directly by improving the functioning of central nervous system, but indirectly by improving the various factors on which the speed performance depends, like mobility of the nervous system, explosive strength, techniques, biochemical reserves and metabolic power, flexibility, psyche factors. Now we are going to discuss mobility of the nervous system. During all speed performances, the muscles have to contract and relax at maximal possible speed. Example in sprints. This rapid contraction and relaxation of muscles is possible only if the concerned motor center in the CNS can undergo rapid excitation and exhibition. This is called the mobility of nervous system. When this rapid excitation and exhibition of motor centers take place at maximal speed and for some second, then the excitation process tends to separate to the neighboring motor centers, causing unnecessary tension in the body and thereby resulting in deterioration in speed performance. The mobility of the nervous system is trainable to a limited extent. This seems to be determined to a great extent by genetic factor. When muscle contract and relax rapidly in a definite sequence, then the nervous system tends to adapt to this, thereby resulting in speed barrier. Next one, explosive strength. The speed performance depend to a great extent on explosive strength of the muscle concerned. This fact is especially vital for speed performances in which some resistance has to be tackled. Because of the importance of explosive strength and its high trainability, most of the time speed performance are improved by improving explosive strength. Explosive strength further depends on muscle composition, muscle size, and muscle coordination. Example, inter and intramuscular coordination. It also depends on metabolic process. Except muscle composition, all other factors can improve through training. The relative proportion of fast twitch and slow twitch fibers determines to a great extent the maximum possible speed with which a muscle can contract. But this is not trainable as it is genetically determined. Good sprinters have a very high proportion of fast twitch fibers, whereas endurance athletes have a very high proportion of slow twitch fibers, according to Hartman and Tunman, 1986. Sprinters have fast twitch fibers up to 90% in soleus muscle, whereas long distance men or long distance athletes have slow twitch fibers up to 90% in the same muscle. The muscle composition, however, the characterized by high intermuscular and individual differences. Technique. Technique is an important factor determines speed performance. Unlearned movement cannot be done at high speed. This is particularly applicable to complex and difficult movements. Moreover, good technique enables the sportsman to fully utilize his strength and flexibility, etc., to achieve high speed. The movement speed in gymnastics, combat sport, etc., is highly dependent on technique or skill. Like explosive strength, technique is also very commonly an aim of training for improving speed performance. Next one, biochemical reserve and metabolic power. For maximal speed performance, the muscles need high amount of energy at a very high rate of consumption. For this purpose, the phosphagen stored in the muscle should be enough. Moreover, the metabolic process of energy production must take place at a very high pace. For this purpose, sufficient amount of non-oxidative enzymes is essential. Acceleration ability, locomotor ability, and speed endurance are particularly depend on the biochemical reserve and metabolic power. Flexibility. Flexibility includes the stretchability of the muscles and mobility of the joints. Good flexibility allows for optimum range of movement without much internal resistance. thereby positively affecting speed. Flexibility also enable full utilization of explosive strength. Low flexibility lead to excessive internal ranges, muscle tension, and less than optimum strength applicable. Next one, psyche factor. Speed depends considerably on certain psyche factors. Important among these are optimum arousal and motivation, attention and concentration, ability to relax, and the ability to maximally mobilize oneself for a short duration. In addition to these factors, the anticipation ability is of high importance for quick reactions. The ability to relax the non-contracting body part and muscle has been found to be of high importance for speed performance, especially acceleration, locomotor, and speed endurance abilities. But unfortunately, this ability seems to depend much on the central nervous system, and as a consequence, it cannot be significantly improved. Speed principles. Choose a reasonable goal for your event and then work on running at velocities which are actually faster than your goal over short work intervals. Train at goal pace in order to enhance your neuromuscular coordination, confidence, and stamina at your desired speed. At first, utilize long recoveries, but as you get fitter and faster, shorten the recovery period between the work interval to make your training more specific and realistic to racing. The topic will continue in the next slide. Work on your aerobic capacity and lactate threshold. Conduct some easy pace runs to burn calories and permit recovery from the speed sessions. Work on your mobility to develop a range of movement. For example, range of motion at your hips will affect your speed and assist in the prevention of injuries. We are thankful to all book writers and publishers, also thankful some internet sites to help us preparing this presentation. Good morning, everyone. Myself, Deepak Dhava, athletic coach. Today we will discuss plyometrics. Plyometrics. What is plyometrics? Plyometrics, also known as plyos, are a type of exercise designed to produce fast and powerful movements. They are generally used by athletes to improve performance in sports, especially those are involved speed, quickness, and power. In addition, it is possible to find plyometrics used in the fitness field, but to a much lesser degree. Thus, plyometric exercises are explosive, fast-acting movements to develop muscular power and to improve overall speed. In other words, it's exercise that allow muscles to exert maximum force in the shortest amount of time possible. Plyometrics used in weightlifting, powerlifting, volleyball, basketball, athletics, especially in jumping exercise. Plyometrics incognito. Plyometric training, strength training, speed training are not separate motor qualities. Initially, it's called shock training, also called depth jump and intense jump exercise. According to Franz Bosch, speed, stamina, and coordination may be so closely linked that no clear, generally applicable training strategy can be devised on the basis of distinctions between basic motor properties. A spectrum of overload ranking of plyometric intensities: altitude drop, depth jump, drop jump, multi jump like standing triple jump, maximal multi response jump like hurdle hop, sprinting, or hurdling, short throw or multi throw, some maximal multi response jump, skipping, hopscotch, jump rope, jogging, race walking. Overload during plyometric exercise. There is three types of overload during plyometric exercise: muscular or tendon, reflexive, motor learning, variability. Anatomy of depth jump, the foundational plyometric. Stand on a scale and perform a squat. It might say 400 to 600 lb during the reversal of movement. Stand on top of a 36-inch box and drop down into a scale for a peak movement in time. That scale will be read 1000 lb or more. It's all a functions of overload. Depth jumps provide a overload that is evenly distributed through the legs, spine, trunk, and limbs, where verbal training does not evenly distribute force. Verbal are playing checkers, while depth jumps play chess as far as jumping in concern. Eccentrics. The eccentric portion of muscle loading can store 140 to 160% of the force that can be displayed in the concentric portion. Much of the muscle action during plyometrics is explosive isometric. This is an important consideration in light of drop jump, altitude jump, double leg hurdle hop, single leg hurdle hop. The detailed explanation of these points will be discussed in coming slides. Look into the diagram for the difference between advanced and beginner depth jumps. Depth jump or drop jump. You can fine tune the projection angle of the drop. You can fine tune the nature of overload, like 12-inch box versus 48-inch box. You can fine tune the overcome goal, which gives a huge sensorimeter boost to task and improve power output. How to perform depth jump? Stand on the box with your toes close to front edge. Steps from the box and drop to land on the wall of both feet. Try to anticipate the landing and spring up as quick as possible, or rebound back as quick as you can. Keep the feet touchdown time on the ground to the shortest possible. How much? 1 or 3 sets using 6 to 8 boxes. Allow a full recovery between each set. The height of box should be again of 30 cm to 80 cm. Quality of depth jumping is far more important than quantity. Box jump. How to perform the drill? Assume a deep squat position with your feet shoulder width apart at the end of the row of boxes. Keep your hands on your hips or behind your head. Jump onto box, landing softly in a squat position on the wall of feet. Maintaining the squat position, jump off the box onto the ground, landing softly in a squat position on the walls of the feet. Jump onto the next box or so on. Keep the feet touch down time on the ground to the shortest time possible. How much? 1 or 3 sets using 6 to 8 boxes. Allow a full recovery between each set of the height of the box should be in the region of 30 to 80 cm. Quality of box jumping is far more important than quantity. Double leg hurdle hop. It's a common plyometric exercise. Do them over a hurdle. Explosive reaction with both legs develop explode quality. Do them in soft or cushioned surface. How to perform the drill? Jump forward over the barrier with your feet together. The movement should come from your hips and knees. Keep your body vertical and straight. And do not let your knees move apart or to either side. Tuck both knees to your chest. Use a double arm swing to maintain balance and gain height. You should land on the ball of feet, allowing energy to be stored by the elastic component of the leg muscles and immediately take off again. Keep the feet touch down. Time between hurdle to the shortest time possible. How much? 1 or 3 sets using 6 to 8 hurdles. Allow a full recovery between each set. Hurdles should set up in a row, spaced according to ability. The height of hurdles should be in the region of 12 and 36 inch height. Quality of hurdle hopping is so far more important than quantity. Single leg hurdle hop. In single leg hurdle hop, ground contact time is longer than double leg hurdle hop. Can actually have more transfer to two leg jumps of the run due to this nature. Build the explode quality. Do them over a hurdle. How to perform the drill? Stand on one leg. Push off with the leg you are standing on and jump over the hurdle, landing on the same leg. Use forcefully swing to the opposite leg and try to get maximum height to clear the hurdle. You should land on the wall of it, allowing energy to be stored by the elastic components of the leg muscles and immediately take off again. Try to keep your body vertical and straight. Perform this drill by one leg, but both legs separately. How much? 1 or 3 sets using 6 to 8 hurdles. Allow a full recovery between each set. Hurdles should set up in a row, spaced according to ability. The height of the hurdle should be again of 12 to 36 inch height. horizontal parametrics. Multi-jump like standing triple jump, standing broad jump, short or medicine ball throw for distance, back, front, sideward, etc. Bound from various running. The detailed explanation of these points will be discussed in coming slides. Multi-jumps or standing triple jump. A practice jump is permitted so that the athlete can determine their takeoff line. The athlete must stand with both feet behind the selected takeoff line, usually with one foot in front of other. They are allowed to crouch or have a rocking motion leading up to the jump. The free leg may be used to generate momentum by raising the knee up and down, while the takeoff foot can be rocked from heel to toe as long as some part of the foot remain in contact with the mat or ground. The hop involves in one foot takeoff with the athlete landing onto the same foot. Then a step is taken onto the other foot. Then the jump is performed by finally landing with both feet. If the athlete step back after landing or fall back or touch the mat or floor behind their heel, no jump is recorded. Measurement is taken from the takeoff line to the back of the closest hill on landing. Standing triple jump is most popular exercise to develop leg strength or overall leg strength. Standing broad jump. The athlete stands behind the line mark on the ground with feet slightly apart. A 2-foot takeoff and landing is used with swinging of the arms and bending of the knees to provide forward drive. The subject attempts to jump as far as possible, landing on both feet without falling backward. How to perform standing broad jumps? Initiation. Arms swing back, hips hinge, legs core engaged, weight shifted forward. In starting position, concentric contractions of leg and core. In air or middle part, hip and knee fully extended. Full shoulder flexion. Try to take CG point at maximum or highest point landing. Hip hinge, knee and ankle flex. Eccentric landing for shock absorption. Short and medicine ball throw. Medicine ball exercise used as part of a plyometric training program to develop explosive movement. Medicine ball training is combination with a program of weight training and circuit training. Can be used to develop strength and power. How to perform medicine ball back throw? The athlete starts by standing facing away from direction they are going to throw, with their heels at the start line. The starting position is with the ball in both hands, held above the head with arm extended. Keeping the arm extended, swing the ball down between legs while flexing the knee. Then, in one motion, the ball is flowing up and back over the head. Several practices may be required to get the best trajectory for maximum distance. The athlete is permitted to fall backward over the line after the ball is released. In front throw, the athlete will start by standing facing towards the direction they are going to throw. Bounce from various running. Bounding is a higher intensity running drill designed to improve efficiency and power. Essentially, bounding is just an exaggerated run with lots of vertical and horizontal displacement. Go for both height and distance with each stride. How to perform the drill? Jog into the start of the exercise. Push off with your left foot and bring the leg forward with the knee bend and the thigh parallel to the ground. At the same time, reach forward with your right arm as the left leg comes through. The right leg extends back and remain extended for the duration of the push off. Hold this extended stride for a brief time. Then land on your left foot. The right leg then drives through to a forward bend position. The left arm reaches forward and the left leg extends backward. Make each stride long and try to cover as much distance as possible. You should land on the sole of the feet, allowing energy to be stored by the elastic components of the leg muscles and immediately take off again. Keep the foot touch down time to the shortest time possible. How much? 1 or 3 sets over 30 to 40 meters. Allow a full recovery between each set. Quality of bounding is far more important than quantity. Single leg hopping. How to perform the drill? Stand on one leg, push off with the leg you are standing on, and jump forward, landing on the same leg. Use a forceful swing of the opposite leg to increase the length of the jump, but aim primarily for height of each jump. You should land on the ball of it, allowing energy to be stored by the elastic components of the leg muscles and immediately take off again. Keep the foot touch downtime to the shortest time possible. Try to keep body vertical and straight. Perform this drill on both legs. Beginners will use a straighter leg action. Advanced athlete should try to pull the heel toward the buttocks during the jump. How much? 1 to 3 sets over 30 to 40 meters. Allow full recovery between each set. Quality of bounding is so far important than quantity. Now we will discuss on plyometrics. First of all, chest bars. How to perform chest bars? This drill requires a partner. Stand facing each other with your feet shoulder width apart and your knees slightly bent. Begin with holding the medicine ball with both hands at chest level, elbows pointing out. Pass the ball to your partner, pushing it off your chest and end with your arm straight. Your partner catches the ball. Allow the ball to come to the chest before passing it back to you. Try to anticipate the catch and return the ball as quick as you can. Keep the catch time to the shortest time possible. How much? 1 to 3 set. Allow a full recovery between each set. 10 to 20 repetitions in every set or each set. Quality of chest pass is far more important than quantity. Incline push-up depth jump. How to perform the drill? 2 mats, 3 to 4 inches height, placed shoulder width apart. A box height enough to elevate your feet above your shoulders when in a push-up position. Face the floor as if you were going to do a push-up with your feet on the box and your hands between the mats. Push up from the ground with your hands and land with one hand on each mat. Push off the mats with both hands and catch yourself in the starting position. Keep the catch time to be shortest possible. How much? 1 to 3 sets. Allow a full recovery between each set. 10 to 20 repetitions per set. Quality of push-up is far more important than quantity. Next point, power drop. How to perform the drill? This drill requires a partner. Lie supine on the ground with your arms outstretched. Your partner stand on the box holding the medicine ball at an arm length. Your partner drop the medicine ball into your hands. Catch the ball with elbow bend. Allow the ball to come toward your chest. Extend the arm to propel the ball back to the partner on the box. Keep the catch time to the shortest time possible. How much time or how much? 1 to 3 set. Allow a full recovery between each set. 10 to 20 repetitions per set. Quality of vertical toss is far more important than quantity. Next one, vertical toss. How to perform the drill? This drill requires a partner. Sit in front of the box with your back to it, legs separate apart and straight. The other person or partner stands on the box holding the medicine ball over you. Your partner drop the medicine ball into your hands, catch the ball with elbow bend and toss it back over your head to the partner on the box. Keep the catch time is the shortest possible. 1 to 3 set. Allow a full recovery between each set. 10 to 20 repetitions per set. Quality of vertical toss is far more important than quantity. Fifth point is incline chest pass. How to perform the drill? Work with a partner and sit facing each other. Lean back at a 45-degree angle, keeping your abdominal tight. Begin your holding the medicine ball with both hands to chest level. Allows pointing out. Pass the ball to your partner, pushing it off your chest and ending with your arm straight. Your partner catch the ball. Allow the ball to come to the chest before passing it back to you. Try to anticipate the catch and return the ball as quick as you can. Keep the catch time to the shortest possible. 1 to 3 set with 10 to 20 repetitions per set. Allow a full recovery between each set. Quality of chest pass is important rather than quantity. General plyometric exercise. Squat jump, tuck squat jump, lateral jump, power skipping, alternate leg bounding, box jump, vertical step jump, plyometric push-up, standing broad jump, straddle jump, launch jump. Now, specific plyometric exercise. Depth jump, we discussed earlier. Altitude jump, drop jump, multi jumps, maximal multi-response jump, or hurdle hops, sprinting or hurdling, or sprint hurdling, short throw and multi-throw, sub-maximal multi-response jump, skipping, various level of skipping, hopscotch, jump rope, jogging, and race walking. Safety during plyometric exercises. Plyometrics are recommended only for well-conditioned athletes. Proper warm-up before starting plyometric exercise. You should have high level of leg strength prior to performing plyometric. Slowly increase level of intensity and complexity. Land softly to absorb shock. Start slow with small jumps and gradually build up. Allow plenty of rest between plyometric workouts. Stop immediately if you feel any pain in your joints. Use footwear with plenty of cushioning. Perform plyometrics on soft and cushioned surface. Recommended grassy or synthetic surface. Benefits of plyometric exercise. Individuals should be well conditioned with sufficient strength and endurance. Explore athletic abilities free of pain from any injury or condition. Exhibit coordination ability. Plyometrics are not designed to be an exclusive training program. We are thankful to all book writers and publishers and some internet sites to help preparing this presentation, and also thank to all preparing internet sites and we are thankful to all book writers and publishers and some internet sites to help preparing